For bootstrapping the trading runtime, the file brings an OS, so the launcher can read environment variables and perform basic path or process operations at startup, and logging, so the entry point can configure and emit the runtime diagnostics and audit trail needed during strategy execution. It imports Flask because the entry point creates the web application that exposes the control and status REST surface used to interact with the engine. The three configuration accessors get broker app config, get server config, and get system config are pulled from config, so the entry point can load broker-specific credentials and mappings, server binding and runtime HTTP behavior, and global system flags before initializing services and the strategy. The REST handler classes Home API, BrokerLogin API, StartAlgo API, Positions API, and Holdings API are imported, so the Flask app can wire up the control endpoints that let an operator land on the home page, perform broker login, kick off base strategy to run, and query live positions and holdings. This follows the project pattern of modules importing logging and configuration helpers, compared with other modules that import Flask.views, method view, and core controller to implement view logic or modules that pair get broker app config with broker-specific login classes. The entry point focuses on creating the Flask app and wiring in pre-built API handlers while also loading server and system configuration, because it coordinates both the HTTP control surface and the runtime environment. This line creates the Flask application object, named app using the Flask class, so the entry point can expose an HTTP surface for runtime monitoring and control. In the context of the entry point that bootstraps server and broker configuration and then calls base strategy.run, app becomes the WSGI app and request dispatcher that will host health, metrics, and control endpoints the trading runtime relies on. Later lines interact with this same app to set runtime options via app config, to wire endpoints like Home API with add_rule, and start the server with app run. So this instantiation is the foundational piece that makes those web-facing integrations possible while the strategy and execution components are running. After the Flask application object is created earlier, the code sets the Flask application's debug configuration flag to true, which tells the Flask runtime to run in debug mode for this process. In practical terms, this enables the development time conveniences that Flask exposes, more verbose exception tracebacks, and the automatic reloader, so changes to application code restart the server without a manual restart. Within the entry point's bootstrapping sequence, this is one of several environment configuration steps, alongside initializing logging within init Kong and emitting the server config via logging.info that prepare the runtime so the rest of the startup, loading broker and server configurations, and eventually invoking base strategy.run, runs with development-friendly behavior. When the entry point finishes setting up the runtime, it registers an HTTP route on the Flask application by wiring the base URL to the Home API class-based view, so that requests to the server root are handled by Home API. The view is exposed under the logical name Home_API, so other parts of the system or external tools can reference it. This is the same registration pattern used elsewhere in the file. Add_rule binds a path to a class-based view produced via as_view. However, this particular registration targets the base /endpoint, typically used for a landing page or health/status check, whereas the similar registrations for Holdings API, Positions API, and StartAlgo API expose specific runtime and control endpoints for holdings, positions, and starting the algorithm respectively. During application bootstrap, the entry point wires up an HTTP route that exposes the Zerodha broker login flow. It registers the /apis/broker/login/Zerodha path, so incoming requests for broker authentication are dispatched to the broker login API class-based view, registered under the logical name broker_API. This follows the same routing pattern used for other endpoints like Holdings API, Positions API, and Home API, where add_rule maps paths to view classes created via as_view. The difference here is that broker login API is responsible for initiating and handling the Zerodha-specific authentication sequence, so the broker adapter can obtain or refresh credentials that the connectivity and execution layers need before live trading begins. The route is set up during the same server bootstrapping phase when logging, configuration, and other API endpoints are initialized, ensuring the UI or automated components can trigger broker login as part of startup or runtime operation. As the entry point exposes HTTP controls to the runtime, this line registers a route that lets external clients trigger the Algo engine start. It maps the URL for starting an algorithm to the StartAlgo API view handler and gives that handler the logical name StartAlgo API. In the flow of the application, this endpoint is the operator-facing control that transitions the system from initialized to active by invoking the strategy execution path, eventually calling base strategy.run. So the strategy can subscribe to market data, evaluate signals, and submit orders through the broker adapter. This follows the same registration pattern used for the other endpoints in the file: Home API, Positions API, Holdings API. But unlike those read-oriented endpoints, the Start Algo API performs a state-changing orchestration to kick off live trading. The line registers an HTTP route on the Flask application that exposes the runtime's current trade positions via the Positions API class-based view. During startup, this wiring converts Positions API into a callable endpoint by using its as_view factory and binds that handler into the app's routing table so external consumers, like the web dashboard, monitoring tools, or internal REST clients, can request the live positions while the strategy is running. This follows the same registration pattern used for Holdings API and Home API, and for Broker Login API on the Broker Login route. Each call turns a class-based view into a handler and maps a specific path and endpoint name into the server during Bootstrap. The Positions API registration specifically provides access to the active position state rather than holdings, the home page, or Broker Login flows. During startup, the entry point registers an HTTP route that exposes current portfolio holdings to external callers by wiring the /holdings path to the Holdings API class-based view. Concretely, the app creates a callable from Holdings API and attaches it under an endpoint name so the server can route incoming requests to that view. The view in turn will fetch and serialize the live holdings data from the trade lifecycle layer or broker adapter so dashboards and monitoring tools can query the running system. This follows the same registration pattern used for the Positions endpoint, Positions API, the root/home endpoint, Home API, and the Broker Login endpoint, Broker Login API. The difference is purely the route and the domain responsibility. Holdings returns aggregated owned instruments and cash balances. Positions returns active trade positions. Home serves the base UI/health. And Broker Login handles authentication. The route is set up during Bootstrap, so the API surfaces are available by the time the strategy is started, base strategy.run, enabling real-time observability and control while the trading runtime executes. The entry point stores the runtime configuration into the server config variable by calling getServerConfig, so the process has a single, concrete set of server settings to drive initialization. GetServerConfig performs file I/O. It reads the server.json file from the project's config area and returns the parsed JSON as a dictionary, and assigning that return to serverconfig makes those values available to the rest of the startup sequence. Those values are then used immediately to configure runtime details such as the deployment directory, logging, and server port. You'll see later where deploy_dr and port are read and where server config is logged, and they're the authoritative source for helper functions that persist or load runtime state. Get timestamps data and save timestamps data. Use server config to build a timestamps file path. And other subsystems like instruments.fetch instruments from server and trade manager register strategy. Also called get server config when they need the same environment paths. In short, the assignment captures the server configuration early, so the entry point and subsequent components, including the call in a base strategy.run, operate with a consistent configuration context. The configuration loader brings in JSON to parse and emit the JSON blobs that represent server settings, broker app settings, and the persisted timestamps used across authentication, controller, and instruments logic, and it brings in OS to interact with the host environment and file system. Locating config files, expanding paths, creating or checking directories, and reading/writing the timestamp files. Other modules in the code base follow a similar pattern but add more dependencies. For example, controller or startup code typically imports OS and JSON alongside logging and then pulls in functions from config. Configs such as get server config, get timestamps data, and save timestamps data to access the data this file provides. Orchestrator code imports controller and utils to wire components. And model-focused modules import types like segment and product type. The minimal import set here reflects that config's responsibility is low-level file and environment handling for the larger system. Get server config loads and parses the server configuration JSON stored in the project's config directory and returns that configuration as a Python dictionary. It provides the concrete server settings the process needs at startup. Server config is populated by calling get server config and then used throughout the runtime, so values like the deployment directory are made available to other utilities. Get timestamps data and save timestamps data both call get server config to derive the path where timestamps.json is read and written, and many other components, for example instruments that fetch instruments from server, trade manager to register strategy, ticker, and login related code, call get server config when they need runtime paths or flags. The function performs simple file I/O and JSON parsing and follows the same straightforward pattern used by get system config and get broker app config for loading their respective JSON blobs. With server config already populated by get server config, the entry point pulls out the deploy dir value and stores it in the local deploy dir variable, so the rest of the startup sequence has a canonical file system location to work with. That extracted deploy directory is used by subsequent initialization steps to locate or create runtime artifacts, deployment-specific config, broker adapters, timestamp files, and any data folders the engine expects, and to resolve paths when the process sets up its environment and logging. This is the same pattern used a few lines later for log file dir, and is immediately echoed for visibility by the runtime print of the deploy dir, so operators can confirm which deployment path the runtime is using. After get server config populated server config with the runtime settings, this line reads the configured log file directory from server config and assigns it to the local variable log file dir, so the entry point can use that path when initializing logging and any file system steps that follow, like creating the directory or pointing log handlers. This follows the same pattern used for other environment values, such as deploy dir and port, and the value is later echoed to the console by the print statement you already saw. After server config was loaded into server config and deploy dir was extracted from it earlier, this line prints a labeled, human-readable echo of the deploy dir value to standard output, so an operator or startup log can immediately see which deployment directory the runtime will use. In the startup narrative of the entry point that bootstraps configuration, environment, and logging before handing control to base strategy to run, this print serves as an early, side-effect-free confirmation of a critical path setting. The same simple read-then-echo pattern is used for log file dir a few lines later. Log file dir is read from server config and then printed. But these prints write to stout as immediate startup feedback prior to the full logging subsystem being initialized. After server config was loaded and log file dir was pulled out of it, the entry point emits the log file dir value to the process console, so an operator or log collector can immediately see where runtime logs will be written. This is the same pattern used when the code prints deploy dir earlier, and it happens just before init logging kong is invoked with a log file path composed from that directory, making the printed line a simple startup visibility checkpoint that ties the loaded configuration to the logging initialization that follows. After server config is read and the log file dir value is printed, the call to init logging kong with the path built from log file dir and the app log file name establishes the process-wide logging sync that the rest of the runtime will use. Init logging kong configures Python's root logging so that messages are written to that file, formats each entry to include a timestamp followed by the textual message, and sets the severity threshold to info with a human-readable date format. The function itself returns nothing. Its purpose is to ensure that subsequent logging calls, such as the logging.info call that follows, will end up persisted in the configured log file under the runtime's log directory. In the context of the Algo trade framework, this guarantees that broker adapters, market data ingestion, strategy execution, and the order manager produce a consolidated, time-stamped audit trail for debugging, monitoring, and post-trade analysis. Init logging kong is a small bootstrapping helper that centralizes how the process emits runtime logs. When the entry point hands it the path to the application log file, it configures Python's logging system to write messages to that file, to include a standardized timestamp and a message body, and to filter output at the info level. Its effect is to make all subsequent logging calls, such as the early recorded server config and broker app config messages, land in a single, time-stamped log file with a consistent date format, so runtime events, authentication steps, strategy lifecycle messages, and order activity are persisted for troubleshooting and auditing. Conceptually, it is a thin wrapper around the standard logging configuration API that sets file name, message format, date format, and log level, so the rest of the framework can simply use logging.info/debug/error and rely on a consistent, file-backed logging destination. As the application entry point initializes the runtime, the call to logging.info emits the contents of server config into the process logs at info level, so operators and developers can see exactly which server settings were loaded by get server config. This gives immediate startup visibility, confirming environment flags, directory paths, log, and persistent settings, and any other server-level options before those values are used to drive behavior. Because the route registrations you already saw depend on the runtime configuration, and the port value is later read from server config. Having a recorded snapshot of server config makes it straightforward to correlate what the service intended to use versus what it actually bound to. The line plays the same role as the similar logging of broker app config. Both produce human-readable checkpoints of configuration state, while the later assignment of port consumes one of the values from the already logged server config. After the earlier step that loaded server config, the entry point calls get broker app config to populate broker app config with the broker-specific application settings. The runtime needs to initialize connectivity and authentication with an exchange adapter. Get broker app config performs file I/O to read and parse the broker app.json configuration file and returns the resulting JSON object. The return dictionary is then stored in broker app config, logged immediately afterward, and later consumed by the controller helpers, including get broker name and the broker login handlers, as well as the broker adapter initialization code. So the strategy and execution layers start with the correct broker credentials, endpoints, and app-level flags. This follows the same pattern used earlier when the code loaded server config. Centralized JSON config is read at startup and kept in a single variable for the rest of the runtime to reference. Get broker app config is the small startup helper that reads the broker application settings from the project's broker configuration file and returns them as a parsed JSON object for the rest of the runtime to consume. During initialization, the entry point calls get broker app config and stores its result into broker app config, so the controller and authentication flow have a single source of truth for broker name, client ID, app key, app secret, and redirect information. Broker app details uses those values to populate its instance fields, and the broker-specific login implementation, such as Zerodha login, consumes them to perform the actual login handshake. The function performs simple file I/O. It opens the broker config file, parses the JSON, and hands the resulting dictionary back to the caller, following the same pattern used by get server config for server settings. At this point in the entry point, after init logging Kong has established the process-wide logging sync, and after get broker app config populated broker app config with the broker-specific settings, the logging.info call writes the contents of broker app config into the application log at info level, so operators and developers can see exactly which broker application settings the runtime will use for connectivity and authentication. This mirrors the earlier server config emission and provides the same startup traceability for broker-side configuration before the strategy is started. The entry point extracts the port setting from server config and stores it in the local variable name port, so the startup sequence knows which TCP port the runtime should use when it brings up its network-facing components, for example the management/API endpoint or any telemetry socket the engine binds. This is the same configuration read pattern you saw earlier, where get server config produced server config and the log file dir value was pulled out. Here the code mirrors that approach by pulling another runtime parameter from the parse server configuration, so subsequent initialization steps can pass a concrete port value into the server/engine that will be started. The app run invocation starts Flask's built-in HTTP server bound to the loopback interface using the port value that was read into port from server config. Because app was instantiated earlier with Flask and its debug flag set, calling app runhands control to Flask request loop, so any routes and view functions registered on the Flask application become live and begin handling incoming HTTP requests. In the context of a startup sequence that already initialized logging with init logging Kong and loaded broker settings with get broker app config, app run makes the runtime's HTTP control and observability surface reachable locally, so operators, the dashboard, health checks, or other local tooling can query runtime state, positions, and control endpoints while the strategy and execution components are running. The call, therefore, both opens the local network endpoint for the service and keeps the process running so base strategy.run and the rest of the trading runtime remain active and reachable. After deploy DR is pulled out of server config, the entry point verifies that the path actually exists on disk. If it does not, the process prints a human-readable message naming the missing deploy DR and then terminates with a non-zero exit status, so the startup stops immediately rather than proceeding into a partially initialized runtime. This is an early startup validation that protects later steps which expect deployed artifacts and configuration to live under deploy DR. Because logging is configured later via init logging Kong, the check uses a plain print to surface the problem to the operator, and the immediate exit ensures supervisors, or CI, see a failure instead of the app continuing in an invalid state. This differs from the nearby lines that simply assign or print deploy DR and log file dir. Those are informational or configuration reads, whereas this is an explicit guard that enforces a required runtime precondition. The entry point verifies that the file system path held in log file dir actually exists by invoking os.path.exists, and if the directory is missing, emits a plain stout message and terminates the process with a non-zero exit. This is a fail-fast precondition that runs before init logging Kong is called, so the runtime never attempts to create or open the application log file inside a non-existent directory, because Python's logging system has not been configured, yet the code uses print for the immediate error message. Compared to the earlier line that simply echoed the log file dir value and the earlier assignment that populated log file dir from server config, this check enforces that the logging sync can be created and forces the application to stop cleanly when that prerequisite is absent. Get system config is the small synchronous helper in the centralized configuration loader that opens the system-level JSON configuration, parses it, and returns the resulting Python dictionary for callers to consume. Its purpose is to expose runtime level. As we saw earlier, when get server config and get broker app config load startup settings and boot the logging sync, get holidays plays the equivalent role for calendar data. It performs a simple file I/O read of the project's holidays configuration and returns the parsed JSON object, so the rest of the runtime can consult official market holidays. Utilities in utils. For example, the functions that generate expiry symbols and the holiday checking helpers used by strategies and the scheduler. Call get holidays to determine whether a given date is a holiday, to skip trading days, and to drive expiry calculations. Like get server config and get system config, get holidays follows the same lightweight pattern of reading a configuration file and returning the deserialized data. Unlike get timestamps data, it does not perform deploy directory resolution or missing file handling. It simply reads and returns the holidays payload for callers to use. Get timestamps data uses the already familiar get server config to locate the runtime's deploy directory, then looks for a timestamps.json file inside that deploy DR. If the file is missing, it returns an empty dictionary, and if the file exists, it opens and parses the JSON and returns the resulting Python dictionary. Conceptually, this is the read side of the timestamps persistence pair that complements save timestamps data. Startup components like instruments fetch instruments from server and trade manager. Register strategy called get timestamps data to learn the last saved timestamps, so they can decide whether to fetch fresh instrument data or resume work without duplicating work. The function performs a simple existence check before doing file I/O, so callers get a safe, empty state when no persisted timestamps are present, and it relies on get server config to centralize where deployment artifacts, including timestamps.json, live. Save timestamps data accepts a timestamps dictionary and persists that runtime metadata as a JSON file inside the deployment directory defined by the server configuration. It first obtains server config by calling get server config, uses the deploy DER value from that configuration to form the path for a timestamps.json file, opens that file for writing, and writes the supplied timestamps object as pretty printed JSON, and then prints a short console message confirming where the file was written. Conceptually, this is the right-side companion to get timestamps data. Components like instruments fetch instruments from server and trade manager, register strategy update, or create timestamp entries at runtime, and call save timestamps data, so authentication state. Last instrument fetch times, and other cross-module timestamps survive process restarts and can be read back by authentication, controller, and instrument loading logic. The observable side effects are file I/O to the deploy DR and a console print for operator feedback. Base strategy pulls together a small set of runtime, domain, and helper modules so derived strategies can read market data, classify orders, interact with the execution layer, and emit lifecycle diagnostics. The logging module provides the process-wide logger that was configured earlier during startup, so strategy events, decisions, and errors are written to the established application log. Time and date time supply, the lightweight timing and timestamp utilities the strategy uses for scheduling, measuring durations, and tagging events as the strategy lifecycle advances. Product type is the domain model enum that lets base strategy label orders and positions with the correct product classification. For example, differentiating intraday versus delivery, which the trade manager and broker adapters rely on. Quotes is the normalized market data accessor that base strategy uses to fetch the current price/quote view for instruments, so strategy logic can make decisions without dealing with broker-specific payloads. Trade manager is the trade lifecycle and execution coordinator that base strategy uses to place, modify, cancel, and query orders, and to reconcile trade state with the strategy's internal bookkeeping. Util supplies shared helper routines, formatting, calculations, small conversions that keep repeated utility logic out of strategy code. This import set mirrors the common pattern you've seen elsewhere in the codebase. Most strategy-adjacent modules import logging and datetime for observability, product type, and trade management primitives for execution semantics, and a small shared utils library, while other files add direction or instruments when they need order polarity or instrument lookup functionality. Base strategy defines the common lifecycle, defaults, and small helpers that every concrete strategy builds on, and it wires each strategy instance in a trade manager, so the engine can track and persist strategy-specific traits. On construction, base strategy captures a name and sets a set of sensible defaults for enablement. Product type, symbols list, stop/target percentages, start/stop/square off timestamps, capital, leverage, max trades per day, F&O flags and capital per set. It then registers the instance with trade manager.register strategy and populates its trades list by calling trade manager.get all trades by strategy, so any previously persisted intraday trades are available to the strategy. It exposes simple identity and enablement accessors. Get name is enabled, set disabled, and a process placeholder that logs invocation and is intended to be overridden by derived classes such as binforb30min, option selling, and sample strategy. Two utility calculators are provided. Calculate capital per trade computes an integer allocation per trade using leverage and a configured max trades per day, and calculate lots per trade returns 0 for non-F&O strategies or derives lot count from capital and capital per set for F&O. Can trade today returns true by default, so strategies can override business day logic. The run method orchestrates the strategy's runtime gating. It skips execution when disabled, consults market state via utils, the market close for the day, and uses utils.wait till market opens and utils.get market start time to defer until market open. Checks can trade today, sleeps until the configured start timestamp using utils.get epoch when necessary, and then enters a loop that exits once utils reports the market is closed. The class therefore centralizes the repeated preconditions and scheduling behavior that concrete strategies reuse while leaving trade generation, placement, and per-tick decision methods to the subclasses and to the rest of the trade manager/utils ecosystem. The imports here bring together a small set of standard library utilities and a couple of domain types that utilities rely on across the framework. Math supplies numeric helpers for calculations used in normalization and risk math. UID is used when utilities need to create unique identifiers for ephemeral objects or test fixtures. And time plus daytime and time delta provide the runtime timekeeping and arithmetic needed for timestamping. Interval calculations and market session logic, calendar, is pulled in to assist with weekday/holiday computations that are combined with the project's holiday data from Get Holidays. You've already seen Get Holidays used elsewhere to load the market calendar. Logging is imported so utility functions can emit diagnostics consistent with the rest of the system. Finally, direction and trade state are the domain enums the utilities use to interpret and normalize trade side semantics and lifecycle state when helpers process trades or build normalized quote/position views. Compared to the similar import lists found in strategy and core modules, which often import product type, quotes, trade manager, or the central utils class. This file focuses on foundational, low-level helpers, stlibtime/math/uid/calendar, plus the minimal domain types, direction, trade state, and holiday loader needed to keep shared normalization and date logic consistent across strategies and tests. Utils centralizes small, commonly used helpers around numeric rounding and market time calculations that other mid-level modules and strategies rely on to make time and price-based decisions. It defines the standard date, time, and date-time formats used across the project and provides two rounding helpers. Roundoff performs a simple two-decimal currency style, rounding used by P&L and price reporting, and round NSE price snaps, an arbitrary price up to the next valid NSE tick by scaling, applying a ceiling and risk scaling, effectively enforcing a 0.05 tick granularity. The market status helpers drive the runtime behavior of strategies and managers. Is market open first consults the holiday logic via the holiday helper in the adjacent utils part, and then compares the current instant to market window boundaries. Is market closed for the day flags that the remainder of the day is non-tradable either because of a holiday or because the current time is past the market close. Wait till market opens computes seconds until the next market start and sleeps while emitting an informational log using the provided context string. It relies on get epoch to convert date times to integer epoch seconds. Get market start time and get market end time are convenience accessors that produce date times set to the official market open and close times by delegating to get time of day, which normalizes any past day time, or now, to a specific hour/minute/second with microseconds cleared. Get time of today is a thin convenience wrapper for constructing those day-specific date times for the current day, and get to date str. Convert to date str is a simple formatter that turns a Python datetime into the project canonical date string using the date format constant defined on utils in utils_part1. So downstream code always compares dates in the same textual form. Is holiday performs the project's holiday logic for any datetime. It first rejects weekends by checking the weekday name, then converts the datetime to the canonical date string via convert_date_str and consults the holidays list returned by getHolidays, which you already saw reads the holidays.json file. If either condition matches, it reports the day as a holiday. Is today holiday is just a convenience wrapper that asks is holiday about the current moment. Generate trade ID returns a unique identifier for a new trade by producing a UUID4 string, which trade uses when instantiated. Calculate trade P&L accepts a trade object and computes and assigns its running P&L and P&L percentage. When the trade is active, it compares the current market price against entry, depending on the trade direction. And when the trade has exited, it uses the recorded exit price versus entry. Numeric results are normalized with util.roundoff, and the percent is computed against the notional entry value. Prepare a monthly expiry future symbol builds a monthly future symbol for a given underlying by first finding the monthly expiry date via utils to get monthly expiry date, logic for which lives in utils_part 3. Then checking whether the current time is beyond that expiry's market end, and, if so, advancing to the next month before formatting the symbol. It forms the suffix from the 2-digit year and the 3-letter uppercase month name and appends the futures marker and emits a log entry with the produced symbol. Prepare weekly option symbol begins the weekly option symbol workflow by resolving the appropriate weekly expiry date using utils.get weekly expiry date from utils_part 3. Compares market start and expiry market end times to decide whether to roll the expiry forward, and supports an explicit number weeks plus offset by shifting weeks and re-resolving the weekly expiry, and then proceeds in the adjacent code in utils_part 3 to construct the option symbol string in the appropriate monthly or day encoded format. This function therefore orchestrates expiry selection and defers the final symbol encoding details to the companion logic in utils_part 3. Utils_part 3 provides the holiday-aware expiry date calculations and the branching logic used to build option symbols that other strategy modules rely on when they need to reference weekly or monthly expiries. The prepare weekly option symbol logic first asks utils.get monthly expiry date for the month's expiry and compares it to the weekly expiry it was already computing. If the weekly and monthly expiries coincide, it formats the options trading symbol using the 2-digit year plus a 3-letter uppercase month abbreviation, strike an option side. Otherwise, it formats the symbol using a compact encoding. Trade Manager pulls together a small set of runtime, domain, and broker-specific building blocks so it can translate strategy signals into executable orders and durable trade records. The standard Python imports OS, logging, time, JSON, and datetime provide file system access, runtime diagnostics, simple timing, JSON serialization, and timestamping needed for persisting trade state and measuring lifecycle events. Get-server-config is used to locate runtime configuration and deploy paths. Recall get-server-config from earlier. While controller gives access to the core runtime context that Trade Manager uses to interact with other engine components. Zerodha Ticker and Zerodha Order Manager are the broker-specific adapters for market data and execution that Trade Manager will call into when it needs live quotes or to place /modify/cancel orders. The trade domain is represented by trade, trade state, trade exit reason, and trade encoder, so Trade Manager can create trade objects, record state transitions, and serialize them for storage or messaging. Order input params and order modify params are the parameter wrappers Trade Manager constructs when building new orders or issuing modifications. An order along with order type, order status, and direction are the shared order model enums and structures used throughout the engine to track the life cycle of individual execution requests. Finally, utils supplies common helpers, formatting, rounding, time helpers that Trade Manager uses for small transformations. This import set follows the same project pattern seen elsewhere, reusing logging, order models, and utils across modules, but differs from the other import blocks by combining configuration and controller access with the trade lifecycle classes and broker-specific order/ticker adapters, reflecting Trade Manager's role as the glue between strategy signals, broker execution, and persistent trade bookkeeping. Trade Manager implements the lifecycle controller that glues strategies to execution. The trade manager class holds runtime state, a ticker instance, the in-memory list of trade objects, a map from strategy name to strategy instance, a symbol to current market price map, the intraday trade directory path, and a list of symbols already registered with the market feed. The run method is the orchestrator that first consults utils to skip startup on market holidays or a closed market and then waits until market open when needed. It then loads the server configuration via get server config to derive a deploy-level trades directory and builds an intraday folder named for today, creating it if absent. After discovering the broker via controller.getBrokerName, it instantiates the appropriate ticker adapter. The code uses Zerodha ticker for the Zerodha broker, starts the ticker and registers trade manager.ticker listener as a tick consumer, sleeps briefly to let the feed stabilize, and then calls load all trades from file to hydrate any persisted trades for today. Load all trades from file looks for a trades.json under the intraday directory, logs and returns if missing, otherwise clears the in-memory trades list, parses the JSON, converts each JSON object into a trade using converting into trade, appends them to trade manager.trades, logs each load and registers the trade's trading symbol with the ticker if that symbol hasn't already been registered. After initialization, run enters a loop that stops once utils reports the market closed. Each cycle it calls fetch and update all trade orders and track and update all trades to reconcile live order state and advanced trade state. Those behaviors are implemented in other trade manager parts, catches and logs exceptions from the cycle, persists the current trades via save all trades to file, then sleeps for a fixed interval before repeating. The register strategy helper simply records a strategy instance into strategy to instance map by its base strategy name so incoming ticks and lifecycle actions can route to the correct strategy. It imports Python's logging so base ticker can emit structured runtime diagnostics for tick processing, error conditions, and lifecycle events, and it imports controller from core. Controller so base ticker can delegate decision-making and lifecycle control to a controller instance rather than embedding that logic itself. In the project's architecture that mirrors the separation of concerns, base ticker provides the feed, event handling, and lifecycle hooks while controller encapsulates the trading control logic. Similar import patterns elsewhere show the same split. Some modules import controller alongside domain models like quote when they need both control logic and data objects, while broker adapters and startup code import configuration helpers and broker-specific login classes, such as getBrokerAppConfig, BrokerAppDetails, or Zerodha login when they must perform connectivity and authentication. This file keeps its imports minimal because its role is to standardize tick flow and controller integration rather than handle broker-specific or model-level responsibilities. Base ticker provides the common runtime contract and share behavior that lets trade manager, test, and broker-specific tickers plug into a single, predictable tick delivery pipeline so the rest of the Algo framework can treat different broker adapters uniformly. On construction, base ticker records the broker identifier you passed and grabs the shared broker login object from controller, get broker login, so every ticker instance starts with the same authenticated context. It also initializes an internal tick listeners list that other components register callbacks into. The start ticker, stop ticker, register symbols, unregister symbols, and on-order update methods are defined as no-ops here because concrete tickers such as Zerodha ticker implement the actual connection, subscription, and order update behavior. Zerodha ticker, for example, uses the broker login to obtain app credentials and access tokens and wires its WebSocket callbacks before calling into base ticker's delivery path. Register listener appends a listener callback to the internal list so consumers like Trade Manager, ticker listener, or test ticker listener can subscribe to live ticks. On new ticks is the distributor. It accepts a sequence of normalized tick objects and iterates through each tick and each registered listener, invoking the callbacks inside a try/except and logging any listener exceptions so a faulty strategy callback does not collapse the feed. The connection lifecycle hooks on connect, on disconnect, on error, on reconnect, and on max reconnects attempt provide consistent logging in a single place for runtime diagnostics. Subclasses map their broker-specific WebSocket events onto these hooks. Zerodha ticker maps its on_connect /on_close /on_error /on_reconnect /on_reconnect to these. In short, base ticker centralizes listener management, standardized event logging, and the handshake to controller-provided authentication, while delegating transport, symbol-to-token mapping, and tick normalization to broker-specific subclasses so the rest of the Stus Algo trade with the master_clean system can consume a uniform tick stream. Controller imports the standard logging facility so it can emit runtime diagnostics and integrate with the project's logging sync. It pulls get broker app config from config. Analogous to the get system config helper you already saw, get broker app config is the config accessor that returns the broker-specific runtime settings controller needs to decide which credentials and adapter to instantiate. Broker app details is the model that encapsulates that broker application metadata in credential fields, so controller can pass a typed object around the rest of the system. Zerodha login is the Zerodha-specific login/session manager that implements the authentication flow, session tokens, and any broker-specific handshake logic. Together, these imports let controller load broker configuration, populate a broker app details instance, and drive Zerodha login to obtain an authenticated connection that controller supplies to quotes, base order manager, and instruments _ part 1. This follows the common project pattern where modules import logging, a configuration getter, and a login/adapter class. Other files use the same pattern, but swap in get system config, kite connect, or base login where appropriate. Whereas controller specifically uses get broker app config and Zerodha login because it centralizes Zerodha connection setup. Controller is the single orchestrator that centralizes broker configuration and authentication, so the rest of the framework can obtain a single, shared broker session and its credentials. When external login flow is triggered, for example by broker login API, handing request arguments to the controller, handle broker login reads the broker application configuration from disk, creates a broker app details instance, and populates it with a configured client identifier, application key, and secret, and records the broker name on a class-level attribute. It then selects and instantiates the broker-specific login implementation based on that broker name. For example, Zerodha login when the broker is Zerodha, and delegates the authentication flow to that login object. The broker login implementation performs the provider-specific session exchange, sets the broker handle and access token on the base login-derived instance, and returns a redirect URL, which handle broker login forwards back to the caller. Controller exposes two simple accessors, get broker login and get broker name, that return the stored broker login instance and the broker identifier respectively. Other parts of the system call those accessors, base order manager to obtain the broker handle for order placement, base ticker to attach market feeds, API endpoints for holdings and positions, instruments for instrument fetches, and trade manager/strategies for runtime needs. So a single authenticated session and configuration are reused across the application. The design uses class-level broker login and broker name as a singleton-like shared state, so the authentication result and broker details become the single source of truth for the rest of the modules. Broker app details is a small value object that holds a broker identifier and the credentials the controller needs to construct an authenticator and broker session. Controller.handle broker login loads the broker configuration via get broker app config and then constructs a broker app details with the broker name. It then calls set client ID, set app key, and set app secret to populate the instance. Those attributes, broker, client ID, app key, and app secret, are the pieces Zerodha login, which extends base login. We'll read through the base login pathway when establishing a broker handle and access token, and there are what other parts of the system rely on when the controller supplies broker-specific parameters for market data, order execution, and trade lifecycle management. The methods on broker app details are simple setters that write those instance attributes. Its role is purely to encapsulate and carry the broker app configuration from the controller into the login and broker adapter layers. Zerodha login pulls in the runtime diagnostics facility via logging, so it can emit the same structured runtime and error messages other modules already use. It brings in kite connect for the kite connect SDK, because this adapter needs the broker-specific client to perform API, key/secret-based authentication, generate request/session URLs, and exchange tokens with Zerodha during login and session management. It reads environment and deployment values through get system config so the adapter can load API credentials, session persistence paths, and other system-level settings rather than hard-coding them into the class. Finally, Zerodha login's subclass is base login, so it can implement the broker-specific parts of the shared login contract and reuse common login/session lifecycle behavior defined by the framework. This import set follows the same pattern seen elsewhere. Logging is reused across modules, but where other files use kite ticker for live ticks, Zerodha login uses kite connect for the authentication handshake, and where some modules pulled get broker app config for app-specific settings, Zerodha login uses get system config to obtain broader system-level credentials needed at startup. Zerodha login extends base login and implements the Zerodha-specific authentication and session setup used by controller to establish a live broker session. Its constructor delegates initialization to base login, so the instance carries the broker app details prepared by controller, a handle broker login. The login method accepts the incoming request arguments and first reads runtime configuration via get-system-config to later construct a post-login redirect. It then instantiates the Kite Connect client using the app key for broker app details. If the incoming arguments contain a request_token, the OAuth callback path after the user has authenticated with Zerodha, Zerodha login exchanges that request token for a session using the app secret, extracts the access token from the return session, configures the Kite Connect client with that access token, and persists the Kite Connect handle and access token onto the base login instance by calling setBrokerHandle and setAccessToken, so controller, the getBrokerLogin, can expose an authenticated broker handle to the rest of the system. After a successful exchange, it builds a home URL using the system config and returns it as the redirect destination. If no request_token is present, the initial login flow. Zerodha login asks Kite Connect for the provider login URL and returns that so the web endpoint can redirect the user to Zerodha's authorization page. Throughout the method, it emits structured logging. The net effect is that once login returns an authenticated Kite Connect placed on base login, downstream components such as base order manager, holdings API, positions API, and the ticker plumbing can obtain an authenticated broker handle via controller, get broker login, and make authenticated API calls on behalf of the user. The file pulls together the small set of building blocks the Zerodha-specific ticker needs to implement real-time market fee behavior. Logging is imported, so Zerodha ticker can emit the same structured runtime diagnostics and lifecycle events you saw used elsewhere. JSON is available to parse or serialize raw messages coming from the streaming layer or to persist/inspect payloads. Kite ticker is the Kite Connect streaming client that provides the WebSocket-based market feed from Zerodha. This complements other files that use Kite Connect for REST operations. But here we need the live tick interface. Base ticker is brought in so Zerodha ticker can implement the shared runtime contract and integrate cleanly with Trade Manager and the rest of the framework. Instrument supplies the instrument metadata and token-to-symbol mapping logic Zerodha ticker uses to translate broker tokens into framework symbols and to look up instrument details. Tick data is the framework's normalized tick model. That Zerodha ticker will populate for every incoming market update, so the rest of the system, strategies, Trade Manager, order managers, can consume a consistent tick shape. This set of imports follows the same project pattern you've already seen. Modules typically combine logging plus a broker SDK client, the appropriate base interface, domain models, and helper metadata classes, while differing from the Kite Connect using modules by specifically depending on the streaming client and the tick data normalization type needed for live tick ingestion. Zerodha ticker is the Zerodha-specific implementation of the base ticker contract that wires live market feed, instrument metadata, and login state into the framework so Trade Manager, strategies, and tests can receive normalized ticks. On construction, it initializes as a base ticker for the Zerodha broker and therefore inherits the broker login handle supplied by controller. When start ticker is invoked, it asks the broker login for the stored broker application details and access token. If the access token is missing, it logs an error and aborts startup. Otherwise, it creates a Kite WebSocket client using the broker app details and access token, attaches the Zerodha-specific WebSocket callbacks, connect, close, error, reconnect, no reconnect, ticks, and order update handlers, records the ticker instance on self, and opens the WebSocket in a non-blocking /threaded mode so the rest of the engine can continue running. Stop ticker performs an orderly WebSocket close. Register symbols and unregister symbols translate framework trading symbols to Zerodha instrument tokens via instruments.getInstrumentData by symbol. Log the token lists, and then call the underlying Kite subscribe/unsubscribe so the broker will start/stop emitting ticks for those instruments. These methods are the bridge used by Trade Manager when a strategy registers its symbols. The on_ticks handler is the normalization step. For each incoming Zerodha ticket, looks up instrument metadata by token, constructs a tick data object with a trading symbol, using the tick data constructor you already saw, and populates the tick data fields from the Zerodha payload, last price/quantity, average price, volume, buy sell queues, OHLC, and change. After converting the whole batch, it delegates to base ticker.onNewTicks, which fans those normalized tick data instances out to registered listeners, such as Trade Manager, ticker listener, or test callbacks. In short, Zerodha ticker performs Zerodha-specific login verification, connection lifecycle management, symbol token mapping, raw to uniform tick transformation, and subscription control, so the rest of StuSalvo TradePath master_clean can operate on a consistent tick model regardless of the broker. Base login provides the centralized, broker-agnostic container for authentication state and a simple contract that broker adapters implement to establish a live session. When an instance is created, it keeps the broker app details object and the broker name, so subclasses have the configured credentials and identifier available. The login method is intentionally empty at this level and is overridden by broker-specific classes, such as Zerodha login. Controller, a handle broker login builds the appropriate subclass and calls its login implementation. And that implementation is expected to perform the broker-specific handshake, obtain an API client, the broker handle, and any access token, and then populate base login by calling setBrokerHandle and setAccessToken. Those setters persist the broker handle and access token as instance attributes, while getBrokerHandle, get. Tick data is the lightweight, normalized container the Zerodha adapter uses to turn a raw broker tick into a predictable, numeric object that the strategy, risk, and execution layers can consume. Zerodha ticker maps the incoming broker token to a trading symbol via instruments.getInstrumentData by token and then constructs a tick data for that symbol. The on_ticks path fills the tick data fields so downstream listeners access through base ticker and trade manager receive a consistent shape. The class exposes the canonical per tick fields you expect for real-time decisioning: last traded price and quantity, average traded price, aggregate volume, total buy and sell quantity, and the OHLC, open, high, low, close, plus change, and it initializes all of them to 0 to guarantee defined numeric values during tick delivery. Because it contains only the essentials, tick data is optimized for fast in-memory propagation in the ticker pipeline and for simple checks like price trigger comparisons, volume filters, and short-term movement calculations performed by the controller/strategy code. It mirrors the same domain pattern used across the project for small DTOs, such as order and quote, but intentionally omits the extra derivatives present on quote, for example, open interest and circuit limits, to keep the tick object minimal and fast for live processing. The instruments component brings in standard runtime and persistence helpers. OS is used for file system interactions when reading or writing instrument timestamp and metadata files. Logging is used so instruments can emit the same kind of runtime diagnostics other core pieces produce. Recall controller and trade manager also log. And JSON is used to serialize and deserialize the timestamp/metadata payloads. From config, config it imports get server config, get timestamps data, and save timestamps data, so instruments can read server-level settings and load or persist the cache timestamp/metadata that strategies rely on. Controller from core. Controller is imported so instruments can participate in the same orchestration surface and access controller-level facilities if needed, and utils from utils. Util supplies shared helper routines used during normalization and format conversions. This set of imports follows the project pattern where modules pair file system/config access, logging, controller integration, and utility helpers, but instruments is distinct in that it explicitly imports the timestamp persistence functions rather than broker tickers or order managers found in other modules. After obtaining a list of instruments, instruments_part2 persist that list by calling instruments save instruments, so the normalized metadata is available on disk for subsequent runs. If the list is empty, it prints an error, logs an error, and terminates the process with a non-zero exit code. It then creates two in-memory indices to make lookups efficient for downstream consumers. One that maps trading symbols to the instrument metadata, and another that maps instrument tokens to the same metadata objects. The code iterates through the loaded instrument dictionaries, extracts the trading symbol and instrument token for each entry, and populates instruments that symbol to instrument map and instruments that token to instrument map accordingly. After building these maps, it logs the total instruments count, assigns the full list to instruments list so callers that need the complete array can access it, and returns the list. The two static accessors get instrument data by symbol and get instrument data by token simply return the corresponding entry from those maps, providing binforb 30min, option selling, short straddle binf, Zerodha ticker, and trade manager with fast symbol/token resolution. The persistence call ties back to instruments_part1 behavior, where save instruments updates timestamps and writes the instruments file, and the timestamp helpers and utils functions referenced elsewhere determine when fresh fetches and saves happen. Instruments implements the cache-in-fetch layer that makes normalized instrument metadata available to the rest of the framework, so the ticker, order managers, and strategies can resolve trading symbols and instrument tokens reliably. It keeps an in-memory cache via instruments list, symbol to instrument map, and token to instrument map, and provides the orchestration to load from disk, refresh from the broker, and persist metadata and timestamps. The decision to refetch is encapsulated in should fetch from server, which consults persisted timestamps via get timestamps data and uses utils get epoch to decide whether the last save is missing or older than 24 hours. That logic prevents unnecessary network calls while ensuring daily refreshes. Update last save timestamp writes the current epoch into the timestamp's payload and delegates persistence to save timestamps data, so the refresh decision persists across runs. Load instruments reads the instruments.json file from the deploy DR obtained via get server config, logs when the file is absent, and returns an empty list in that case. Save instruments serializes the supplied instrument list back to instruments.json, logs the save, and updates the instrument's last saved at timestamp immediately after writing. Fetch instruments from server obtains the active broker handle through controller.getBrokerLogin, which ties back to base login, and asks the broker for NSE and NFO instrument lists, combining them and catching/logging any exceptions that occur during the network call. Fetch instruments is the top-level accessor. It returns the in-memory cache if populated. Otherwise, it tries load instruments, and when the on-disk list is empty or should fetch from server indicates a refresh, it calls fetch instruments from server. The rest of the post-fetch work, persisting with save instruments, building symbol and token maps, and failing fast if nothing is available, is performed by instruments_part 2. Overall, instruments_part 1 coordinates when and how instrument metadata is read, refreshed, and timestamped, so the rest of the system, Zerodha ticker, order managers, and strategies, can rely on stable symbol-to-token mappings and avoid unnecessary broker queries. The code continues the trade manager role of gluing strategy signals to execution and bookkeeping by persisting and managing the in-memory trade list, wiring market data to strategy decision logic, and triggering execution when strategies indicate a trade should be placed. Save all trades to file serializes the in-memory trades list to a trades.json file onto the intraday trades DR using the trade encoder and logs the outcome, so the day's state is durable. Add new trade, first guard against a null argument, logs the incoming trade, and prevents duplicates by comparing with existing trades using trade.equals. On successful addition, it appends the trade to the shared trades list, logs the new trade ID, ensures the ticker is subscribed to the trade's trading symbol, registering the symbol with the Zerodha ticker and recording it in registered symbols. And, if a strategy instance exists for the trade strategy name, hands the trade to that strategy via add trade to list so the strategy can track it. Disable trade simply marks a trade as disabled and records a logged reason. Ticker listener receives normalized tick data. Recall Zerodha ticker provides ticks, updates symbol to SIMP map with the latest price, and then for every registered strategy it queries for any untriggered long and short trades for the tick symbol using getUntriggeredTrade. If a trade exists, it asks the corresponding strategy instance whether it should place the trade via shouldPlaceTrade. And when the strategy says yes, it calls TradeManager.ExecuteTrade, which invokes the order manager to place orders, and on success, moves the trade into the active state and stamps its start timestamp using utils.getEpoch. GetUntriggeredTrade scans the central trades list, skipping disabled trades and anything not in the created state, and returns the first trade that matches the given trading symbol, strategy, and direction, which is how the listener identifies candidate trades that are waiting for market conditions to execute. The file brings in a small, focused set of runtime dependencies that let the trade model represent and log its lifecycle. Logging provides the same diagnostic channel other core modules use, so trade can emit runtime messages consistent with controller, trade manager, and instruments. Trade state supplies the canonical lifecycle enumeration that trade uses to track and transition an individual trade through states like new, open, closed, etc. So the trade management layer has a single source of truth for status logic. Product type supplies the contract level classification, for example intraday versus delivery products, that trade uses to compute sizing, margin, and exit behavior according to broker/product rules. Utils provides the shared helper functions used across the project, timestamping, numeric rounding, simple serialization, and other small utilities, so trade can reuse common operations instead of re-implementing them. This import pattern mirrors other modules that commonly import logging, product type, and utils. The difference here is that trade imports trade state specifically because it models lifecycle transitions, whereas other files often pair product type and utils with execution, order, or strategy-specific models like direction or order manager. Trade is the domain object the trade management layer uses to represent one executable position and track its lifecycle, risk parameters, and P&L as strategies, and the manager move it from creation to completion. On construction, a trade is given a normalized trading symbol, a unique trade ID produced by utils.generate trade ID, and a create timestamp from utils.getEpoch, and sensible defaults such as exchange set to NSE and product type set to product type.mis. Those initial fields let strategy code like Benforb 30 min, option selling, sample strategy, and short straddle BNF instantiate trades with minimal boilerplate. The instance fields capture the full state machine and data needed by trade manager and order manager. Requested entry, the price the strategy requested. Entry, the executed price, quantity, and filled quantity. Order lifecycle versus fills. Initial stop loss and stop loss to support trailing SL logic obtained from base strategy that get trailing SL. Target, CMP for the latest market price. Updated from Zerodha ticker on for ticks via trade manager to ticker listener. Trade state starts as trade state.created timestamps for. Start/end and an optional intraday square-off timestamp used by trade manager to track and update all trades to force exits. Flags such as is futures, is options, and option type, plus interactions with utils that prepare monthly expiry futures symbol, utils that get to the date STR, and utils is to the weekly expiry day, let strategy code, and symbol helpers produce correct FNO instrument names when a trade is for futures or options. Placeholders for entry order, SL order, and target order link the trade to order objects managed by the broker adapter and used by trade manager to execute trade and fetch/update flows. Trade manager to convert into trade maps persisted JSON back into trade instances so trade survive restarts and save all trades to file persist them. The equals method implements a practical deduplication/identity check. It first accepts matching trade ID. Otherwise, it verifies key attributes, symbol, strategy, direction, product type, requested entry, quantity, and timestamp to decide if two trade instances represent the same logical trade, which is how higher-level flows avoid duplicate placement. The string method produces a compact, human-readable summary used in logging. Conceptually, trade follows the same simple DTO pattern as order, but while order contains broker order-level metadata and status, trade aggregates lifecycle, risk controls, timestamps, and P&L so strategies. The order manager and trade manager can coordinate execution, trailing SL updates, square-offs, and final exit accounting. Within the base strategy lifecycle, after a concrete strategies process method runs the run loop, enforces a half-minute cadence by computing the seconds remaining to the next 30-second boundary and sleeping that amount so strategies are invoked on a predictable tick rhythm. The should-place-trade method is the standard pre-trade gate used by all derived strategies. It returns false for a missing trade, disables and rejects any trade with zero quantity by delegating to trade manager a disabled trade, which persists the disabled state. Checks the strategy stop timestamp, set by subclasses such as Benforb 30 min and option selling, and disables new trades when the cutoff time is reached. And consults trade manager.get number of trades placed by strategy to enforce max trades per day, disabling the trade if the daily limit is hit. Only when all these checks pass does it allow placement. Add trade to list is a small helper that appends a non-null trade into the strategy's local trades collection that was populated from trade manager. Get all trades by strategy during initialization. Get quote centralizes quote access for strategies by delegating to quotes.getQuote with the strategies is FNO flag, so the same call returns normalized market data, whether the symbol is cash or derivatives. Get trailing SL is a simple overridable hook that returns 0 by default. Concrete strategies, for example short straddle BNF, override it to provide dynamic trailing stop logic that trade manager, the track and update all trades can use. Together, these methods provide the standardized decision points and utilities that wire a concrete strategy into trade manager, quotes, and the runtime, timing expectations of the Algo framework. The file pulls in 3 things it needs to perform the quotes role. A logging facility so it can emit the same runtime diagnostics other core pieces produce. Controller and trade manager also log. The controller so quotes can hook into the framework's centralized runtime services, connection/authentication state, event dispatch and feed wiring, and register handlers for incoming market data. And the quote model so incoming raw ticks can be normalized into the predictable quote objects that strategies and tests will consume. This mirrors a common pattern you've seen elsewhere, where modules import logging and controller to participate in the shared runtime. Unlike some files that also bring in configuration or broker-specific login adapters, Quotes keeps its imports minimal, just a controller for runtime integration and a quote class for shaping outbound data. Because its responsibility is focused on feed handling and normalization rather than configuration or login orchestration. Quotes provides the mid-level adapter that sits between the controller-managed broker session and the rest of the framework, tests, and strategies by turning a broker-specific quote snapshot into the framework's normalized quote object. Its static getQuote method first asks controller for the active broker name, and then fetches the authenticated broker handle from controller to get broker login, relying on the base login managed broker handle that was created during login. For the Zerodha path, it composes the exchange prefixed instrument key, depending on the F&O flag, calls the broker handle's quote method to retrieve the raw broker payload, and then constructs a quote instance and copies the relevant numeric fields from the broker response into the quote. Last traded price/quantity, average price, volume, buy sell aggregate quantities, the nested OHLC values, net change, open interest, day, high/low, and circuit limits. If the active broker is not recognized, the method returns none. The static getCMP method is a thin convenience wrapper that returns last traded price from getQuote or 0 when no quote is available. Strategies and helpers, for example, base strategy to get trailing SL and test miscellaneous. Call getCMP/getQuote to obtain a consistent numeric current market price or a normalized quote object without needing to know Zerodha's payload shape. Quote is the lightweight, broker-agnostic data container that represents a single instrument's market snapshot for the rest of the engine to consume. Its constructor records the provided trading symbol and initializes a fixed set of numeric attributes. For example, last traded price, last traded quantity, average traded price, volume, total buy quantity, total sell quantity, open, high, low, close, change, OI day high, OI day low, lower circuit limit and upper circuit limit, to 0 so downstream code can rely on predictable numeric values even when a broker returns partial data. In the runtime flow, quotes.getQuote obtains the broker name from controller and the broker handle from base login, recalls Zerodha ticker, and base login provide the live feed and login contract, fetches the raw broker quote and maps broker fields into a quote instance. This mapping is what normalizes broker-specific payloads into the uniform quote shape. Because quote mirrors most of tick data's price/size fields, but also carries open interest and circuit limit fields, it serves as the richer snapshot that components such as base strategy to get trailing SL, the order manager, the quotes aggregator, and test, the ticker listener use directly. Helper methods like quotes.getCMP then simply read last traded price from quote or fall back to 0 to supply a current market price. Trade Manager _Part 6 continues the lifecycle orchestration responsibilities by implementing helper actions used when exiting or querying trades and by selecting the concrete order manager for execution. Cancel target order ensures any outstanding target order for a trade is only acted on if it exists and is not already canceled, then delegates the cancellation to the order manager and logs errors or successful cancellation. It relies on the same order manager abstraction that Trade Manager _Part 3 used to place entry orders and that Zerodha Order Manager implements. Set trade to completed centralizes the finalization of a trade. It flips the trade state to completed, records the numeric exit, and preserves any previously set exit reason if present. Stamps the end time using utils.getEpoch, recomputes P&L via utils, calculate trade P&L, and emits a summary log so bookkeeping and downstream reporting have a single canonical place to mark trade termination. Square Off Trade implements an orderly intraday or forced exit path. It first validates the trade is active, records the exit reason, cancels any still open entry order, and cancels the stop loss using the cancel order logic covered in Trade Manager _Part 5, and then either converts an existing target order into a market exit via the broker adapter's modify market facility or places a fresh market target order via place target order, also in Trade Manager _Part 5. This is how the framework enforces square off and emergency exits across strategies. Get Order Manager is the factory that maps the configured broker name from controller into a concrete order manager instance. In the current configuration, it returns a Zerodha Order Manager for the Zerodha broker, so all higher-level trade actions route to the broker-specific implementation. The import list wires in the small set of building blocks Zerodha Order Manager needs to act as the Zerodha-specific implementation of the order management layer. Logging provides the runtime diagnostics that let the order manager emit the same standardized runtime traces other core pieces produce, so Trade Manager and tests can correlate events. Base Order Manager is the broker-agnostic abstract contract that Zerodha Order Manager implements to translate generic order actions into platform calls and lifecycle events. Order is the normalized in-memory order representation the manager will create, update, and return as it places, modifies, and cancels orders. Product type, order type, direction, and order status are the domain model enums that let the manager map framework-level semantics. Market versus limit, intraday versus delivery, buy versus sell, live order state, to Zerodha API fields, and to track order lifecycle transitions. Util supplies small runtime helpers used by the manager for common tasks such as parameter normalization, numeric rounding, and timestamp/ID handling, so the class can keep its logic concise. These imports follow the same pattern seen in other modules that implement broker adapters or orchestration. Everyone brings in logging, the core order model, and the shared model enums, plus the common utils helpers, so different components speak the same domain language when Trade Manager, tests, or other subsystems interact with Zerodha Order Manager. Zerodha Order Manager is the Zerodha-specific implementation of the order management layer that subclasses base order manager to translate framework order intents into kite/Zerodha API calls and to maintain simple lifecycle metadata for orders. Its constructor calls the base order manager initializer with a broker name, so broker and broker handle are wired from controller-managed login state. That broker handle is the kite client used for all subsequent API calls. When place order is called, it logs the intent, reads the kite client from broker handle, maps engine-level fields from order input params into the broker API parameters, choosing exchange based on the is-F&O flag, converting direction, product type, and order type via the Zerodha-specific converters implemented in other parts, and passing quantity, price, and trigger price. Invokes the broker place order call, and on success wraps the response into an order model instance, stamping order ID, order place timestamp, and last order update timestamp using utils that get epic before returning it. On failure, it logs and re-raises the exception. Modify order follows the same pattern for amendments. It logs, invokes the broker modify order API, and selectively sends only the changed fields, omitting quantity/price/trigger if the new values are non-positive or none. Updates the order's last order update timestamp and returns the updated order object, or logs, and re-raises on error. Modify order to market is a focused modifier that changes an existing order to a market order by calling the broker modify API with the market order type, updates the timestamp and returns the order, or logs, and re-raises on failure. The class consistently uses the shared utility and model pieces, order for the normalized order container, and utils to get epic for timestamps, and delegates broker-specific value mapping to the convert to broker direction /convert to broker product type /convert to broker order type helpers defined elsewhere in the Zerodha Order Manager parts. Overall, Zerodha Order Manager _ Part 1 implements the synchronous place /modify to limit /modify to market pathways and error handling used by Trade Manager and tests, following the same logging and wrap pattern seen in the related cancel and order book sync logic in the other Zerodha Order Manager parts. Order defines the canonical order model that the order management and trade lifecycle layers use to represent a broker-level request and its evolving execution state. Test, Zerodha Order Manager _ Part 1, and Trade Manager _ Part 7 all create, inspect, and update instances of order, so the rest of the engine has a consistent, simple object to work with. When an order is constructed, it copies intent-level fields from an order input params instance when provided. Trading symbol, exchange defaults to NSE, product type, order type, price, trigger price, and quantity, and initializes broker-facing, mutable state to neutral values. Order ID and order status start unset. Numeric execution metrics like average price, filled quantity, and pending quantity start at 0, and timestamps and message fields start empty. Zerodha Order Manager _ Part 1 populates the instance after placement. It assigns order ID and sets order place timestamp and last order update timestamp, and runtime callbacks coming through Zerodha Ticker _ Part 1 and base ticker at on order update order status, filled quantity, pending quantity, average price, last order update timestamp, and message as broker events arrive. Trade Manager routines read and sometimes reconstruct order objects, for example via convert to order, to reconcile trade level state with broker. The import of controller brings the framework's central runtime coordinator into base order manager, so the order manager can participate in the same shared session, event, and dispatch infrastructure that other mid-level adapters use. As we saw when examining quotes, controller is the single place that owns connection/authentication state, event routing, and feed wiring. Base Order Manager imports controller for the same reasons, to query the broker session and auth state, register and receive lifecycle events, order updates, fills, connection changes, and route order requests through the controller's centralized plumbing rather than trying to manage network/session details itself. This follows the common pattern in the codebase where components that implement broker-facing logic import core controller to avoid duplicating runtime orchestration. Files that additionally need data shapes also import model classes, for example, quote, segment, or product type, alongside controller. Base Order Manager is the shared scaffold that sits between the controller-managed broker session and every broker-specific order manager. So it centralizes the common wiring and defines the interface the rest of the engine uses to perform order lifecycle actions. In its initializer, it stores the broker identifier and pulls the active broker API client from controller.getBrokerLogin.getBrokerHandle. Recall baselog.getBrokerHandle we examined earlier, making that authenticated client available to subclasses through the brokerHandle attribute. The class then declares the core lifecycle methods: place order, modify order to market, cancel order, and fetch and update order details as no-op stubs that concrete managers must implement. The trade manager and other runtime pieces call these methods to execute entry orders, update SL/target orders, cancel orders, and reconcile local order objects with a broker order book. Base Order Manager also provides 3 conversion helpers that currently return their inputs. These are the extension points that allow the framework to remain broker agnostic by mapping product type, order type, and direction into broker-specific constants. And you can see Zerodha Order Manager overriding those conversions to map to kite constants. Conceptually, when a strategy requests an execution, Trade Manager gets the concrete Order Manager, which inherits from Base Order Manager. Calls Place Order, the subclass uses Broker Handle to talk to the Broker SDK and returns an order instance. Order fields such as order ID, quantity, filled quantity, and timestamps are populated by the concrete implementation. And later, fetch and update all order details is used to pull the broker order book and reconcile order state back into the engine. The class therefore exists to centralize the authenticated handle and the canonical order management API, so different broker adapters like Zerodha Order Manager can plug in the broker-specific behavior while the rest of the system, Trade Manager, ticker hooks, holdings API/positions API patterns, interacts with a consistent interface. Zerodha Order Manager _part 2 continues the Zerodha-specific order management responsibilities by providing the cancel operation, a reconciliation pass that pulls the broker order book and updates internal order objects, and helper conversions that map framework enums into Zerodha API constants. When an order cancellation is requested, the code uses the broker handle obtained from Base Order Manager, the same broker handle used by Place Order in Zerodha Order Manager _part 1. To invoke the broker cancel flow, log success or failure, and updates the order's last order update timestamp using utils that get epoch, so the framework knows when the last broker side change occurred. Failures are logged and re-raised, so callers like Trade Manager can handle them. The fetch and update order details routine asks the broker handle for the full orders list, logs the result size, then iterates the returned broker orders and matches them to the in-memory order instances by comparing the broker order ID. For each match, it copies quantity, filled and pending quantities, status, price, trigger price, and average price into the order object. Applies the business rule that a canceled order with non-zero fills should be considered completed, increments an update, counter, and logs a summary. This keeps the trade manager's view of entry/SL/target orders in sync with Zerodha, so lifecycle actions, for example those orchestrated by Trade Manager, track and update all trades, operate on current state. The convert to broker product type and convert to broker order type helpers translate the framework product type and order type enums into the specific constants expected by the Zerodha client. These mappings are used upstream by place order and modify order to ensure the API receives broker native values. All of these methods rely on the broker handle set by Base Order Manager and follow the same mapping pattern as convert to broker direction implemented in Zerodha Order Manager _part 3 and the placement/modify logic in Zerodha Order Manager _part 1. Keeping the Zerodha adapter consistent in how it converts framework intent into broker API calls and how it reconciles broker responses back into framework models. Zerodha Order Manager _part 3 provides the broker-specific translation for trade direction, so the rest of the framework can remain broker agnostic. When a strategy or the trade manager produces an order input params with a framework direction, for example, when place order, modify order to market, or cancel order need to call the broker. Convert to broker direction grabs the Zerodha session handle that Base Order Manager initializes via controller and maps the framework long direction to Zerodha's by transaction constant and the framework short direction to Zerodha's cell transaction constant. If the direction is neither long nor short, it yields none. This method is one of the conversion helpers alongside convert to broker product type and convert to broker order type. Implementing the adapter pattern so high-level order logic can call a single API and have the correct broker-specific fields filled before interacting with the Zerodha API. Within the Trade Lifecycle Controller, the methods in Trade Manager _part 5 are the concrete helpers that translate a trade object's intended exit behavior into actual broker orders and bookkeeping updates, tying strategy intent to the Zerodha Order Manager and the trade objects fields. When a target order is observed to be canceled externally, the code pulls the latest market price for the trade symbol from Trade Manager, symbol to SIMP map, marks the trade completed by delegating to Trade Manager, set trade to completed, defined in Trade Manager _part 6, with the exit reason set to target _canceled, and then attempts to cancel any standing stop-loss order. The place order method builds an order input params instance for the trade symbol, flips the direction relative to the trade's entry direction, sets product type and an SL_market order with the trade stop loss as the trigger, assigns the trade quantity, and marks the order as FNO when appropriate. Then hands the parameters to the active order manager via trade manager, get order manager. Place order. It records the returned order onto trade, order, log success, and returns a Boolean indicating placement outcome, logging an error on exceptions. The place target order method follows the same pattern for the profit target. It prepares order input params with the opposite direction, sets the product type, and either market or limit order, depending on the isMarket order flag, assigns price, 0 for market, and quantity, marks F&O when needed, places the order through the order manager, stores the resulting order on trade.target order, and returns success or failure while logging outcomes. Cancel entry order and cancel order are defensive cancel helpers that first guard against a missing order or an already canceled state, then invoke the order manager's cancel operation, catching and logging exceptions and logging successful cancellations. These methods update nothing on the trade object themselves beyond relying on the order manager to mutate order status fields that the rest of trade manager's tracking routines, such as track entry order and track SL order from trade manager_part 4. We'll observe. Overall, these helpers are the mid-layer that map trade-level exit semantics into order input params and cancellations, coordinate with Zerodha order manager conversion routines for direction/product type, and update the trade object's entry/SL/target order references so the lifecycle tracking logic can drive state transitions and P&L calculation. Order input params brings in the segment and product type model classes, so it can tag, validate, and normalize the market segment and product class of every order encapsulates. These are the canonical enums the rest of the engine expects when Trade Manager builds an order request. Using segment lets order input params indicate whether an instrument/order belongs to equity, derivative, or other exchange segments. And using product type lets it express the brokerage product category, for example, intraday versus delivery, so downstream order managers receive a consistent type payload. This mirrors the pattern you've already seen elsewhere. Product type is imported and reused by base order manager, Zerodha order manager, and trade manager_part 6, because the models package centralizes these domain enums for use across connectivity, order management, and lifecycle layers. Order input params is the small, standardized data container trade manager uses to assemble and hand a fully specified order to the order management layer. When a trade manager flow, such as track and update all trades, or the place/cancel flows in trade manager_part 3 and trade manager_part 5, needs to submit or modify an order, it creates an order input params instance with the instrument identifier and then fills in the actionable fields, direction, order type, quantity, price, trigger price, before passing it to the concrete order manager. For example, Zerodha order manager. The constructor establishes framework-wide defaults, so callers only need to supply the values that vary per order. The exchange defaults to the engine's primary market. The instrument segment defaults to the equity segment. The product defaults to intraday MIS. And the instrument level flags market as not F&O by default. Numeric fields start at 0 and text fields start empty. Those defaults reflect the trading platform's typical use case and keep trade manager code concise and consistent. The string representation method produces a compact, human-readable summary of all of those fields so the rest of the system can log or display a single-line snapshot of the intended order before or after submission. Order input params, therefore, plays the leaf utility role of normalizing and carrying order intent into the order manager and works alongside the order modify params, and trade classes. Order consumes an order input params instance to populate persistent order state. Order modify params is used for later edits. And trade holds the broader lifecycle and strategy context around these parameter objects. These imports wire the Benforb 30min strategy into the surrounding framework by bringing in the runtime tools, domain models, base strategy contract, utility helpers, and the trade lifecycle primitives. The strategy needs to generate signals and execute them. Logging provides the same consistent runtime diagnostics other core pieces produce, so the strategy can emit lifecycle and debug messages. Daytime supplies the time primitives used to build the 30-minute opening range boundaries and timestamp trades and decisions. Instruments gives access to instrument metadata and selection helpers, so the strategy can resolve the bank nifty underlying strikes and expiry that the ORB logic targets. Direction and product type supply the domain enums the strategy uses when deciding buy versus sell and which product type to request from the broker. Base strategy is the framework contract this class implements/extends so the strategy can plug into the engine's lifecycle, receive normalized market data, and expose its signals. Utils provides small helpers the strategy uses for common operations, time rounding, price math, etc. Trade is the local model used to represent a candidate or live position with its metadata. And Trade Manager is the orchestration layer the strategy calls to submit, modify, or exit orders and a query lifecycle state. This set follows the same pattern seen in other strategy files. Most import logging, base strategy, utils, trade, and Trade Manager, while including instruments of direction here, because Benforb 30min needs explicit instrument selection and directional enums rather than a quotes adapter. Trade Manager _ part 3 sits in the execution and lifecycle glue layer of Stus Algo Trade Python master _ cleaned and implements the runtime actions that turn a strategy-generated trade into a broker order and then keep that trade updated as broker state changes. When execute trade is invoked for a trade, it first snapshots the current stop loss into initial stop loss, used later by the trailing SL logic found in Trade Manager _ part 4, then constructs an order input params for the trades instrument, fills canonical fields such as direction, product type, quantity, and price, chooses a market or limit order type based on the trade's place market order flag, and marks the request as FNO when the trade represents futures or options. That order input params is handed to the order manager obtained via Trade Manager, Get Order Manager, which delegates to the broker-specific place order implementation, Zerodha Order Manager. Execute trade captures the returned order object into trade entry order, log success, and returns a Boolean outcome, logging and returning failure if the place order call throws. Fetch and update all trade orders is a polling/refresh helper that walks the in-memory Trade Manager trades list, collects any entry, SL, and target order objects present on each trade, and asks the order manager to fetch and update details for that aggregated list so order objects kept on trades reflect the broker's latest state. Track and update all trades is the periodic tracker that iterates active trades and drives 3 subflows. It calls track entry order to reconcile entry order fills and statuses, calls track SL order, the SL placement and completion logic implemented in Trade Manager _ part 4, and track target order, the exit/target logic implemented. Trade Manager _ part 4 contains the runtime monitoring and lifecycle logic that keeps active trades synchronized with broker orders and applies basic exit/risk rules. Track SL order first guards that the trade is active and has a non-zero stop loss. If there is no SL order, yet it delegates to place SL order, covered in Trade Manager _ part 5, to create the broker SL order. If an SL order exists, it examines the order status. When the order is complete, it treats the trade as exited using the SL order average price and sets the exit reason to SL _hit or trail _ hit, depending on whether the stop loss has been trailed since entry. Then marks the trade completed and cancels the target via cancel target order. From Trade Manager _ part 6. If the SL order was canceled externally, it logs an error, uses the current market price from symbol to CMP map as the exit, marks the trade completed with SL _ canceled, and cancels the target. For any other SL order state, it invokes check and update trail SL to potentially move the stop loss. Check and update trail SL looks up the strategy instance from strategy to instance map, and, if present, asks the strategy for a new trailing stop via get trailing SL, base strategy to get trailing SL. It only proceeds when the return new trail SL is a positive, better SL, higher for a long, lower for a short. In that case, it constructs an order modify params with a new trigger price and calls get order manager, .modify order to update the broker SL. On success, it updates trade.stop loss and logs the change, and on failure, it logs an error. Track target order mirrors the order modify params is the tiny, purpose-built data container Trade Manager _ part 4 uses whenever the engine needs to change an existing order on the wire. In the order lifecycle story, a Trade Manager routine, such as check and update trail SL, computes new trade parameters, often using a strategy-provided value from base strategy to get trailing SL, and then creates an order modify params instance to package those new values. New price, new trigger price, new quantity, and new order type, with sensible defaults, zeros, or none. So the rest of the system has a predictable object to work with. Once populated, Trade Manager hands the order modify params to the order management layer, which in the Zerodha adapter is consumed by Zerodha Order Manager, modify order, or modify order market. Those adapters inspect the fields and translate only the non-default values down to the broker API. Order modify params follows the same small DTO pattern you've seen in order input params and order. It exists to normalize and label a specific set of broker-facing parameters and to provide a readable string form for logging and debugging. enabling clear, consistent handoff from trade lifecycle logic to the execution layer. Within the trade lifecycle controller, convert to send a trade is the deserialization path Trade Manager uses to rebuild a trade instance from persisted JSON so the engine can resume tracking and managing that trade after a restart or when reloading state. It begins by creating a trade with the trading symbol so the instance gets the defaults defined by trade. Then overwrites the instance's identifying, configuration, and runtime fields with values from the JSON. Things like trade ID, strategy, direction, product, and instrument flags, requested entry/entry, quantities, and fill quantities, stop loss / initial stop loss / target, timestamps, P&L fields, and exit metadata, effectively reconstructing the exact runtime snapshot the lifecycle. Controller needs to continue processing. For the nested order objects, the deserializer delegates to convert into order, which returns none for absent orders or instantiates an order and populates its exchange, product type, order type, price/trigger, quantities, IDs, status, average/fill info, and timestamps, so the order management layer can resume reconciliation. Convert to send order therefore mirrors how order normally seeds an order when created from order input params, but populates every runtime field from the stored JSON. The get last traded price helper is a thin accessor that returns the current CMP from Trade Manager. Symbol to CMP map for a given trading symbol, which strategies and tracking routines use when recalculating trailing stops or P&L after state load. Together, these methods let Trade Manager load persisted trades, restore their linked order state, so Zerodha Order Manager and the rest of the lifecycle logic, as implemented in the other Trade Manager parts, can continue to place /modify, /cancel, or track fills, and provide quick access to the last traded price for downstream decision points. Utils_part 4 contains two small, strategy-facing helpers that sit in the shared utilities layer and are used by the option strategies to make expiry and strike decisions. Isto for weekly expiry asks utils for the canonical weekly expiry date via get weekly expiry date, which we covered earlier. It compares that expiry to the current calendar day at midnight via get time of today. It returns a Boolean indicating whether today is exactly one calendar day before the weekly expiry. That Boolean is used by option selling and straddle strategies to alter behavior around expiry, for example, to avoid initiating fresh FNO positions the day before expiry. Get nearest strike price converts a raw numeric price into the nearest valid option strike, given a configurable strike interval, defaulting to 50. It does this by coercing the input to an integer, computing the remainder against the strike interval, and choosing the lower multiple when the remainder is less than half the interval or the higher multiple otherwise, producing a deterministic nearest strike value that downstream code can pass to symbol preparation helpers, such as prepare weekly option symbol, when generating option trading symbols. Together, these helpers keep expiry awareness and strike normalization consistent across option selling, short straddle BNF, and other strategy code that needs to select tradable option strikes or gate trades near expiry. The import setup start Algo API as a web-facing control that can load runtime configuration and kick off the algorithmic runtime in the background. Method view supplies the Flask class-based view foundation, so start Algo API can be mounted as a REST endpoint. JSON is used to decode incoming payloads and produce JSON responses. Logging provides runtime diagnostics and event messages from the endpoint. Threading allows the endpoint to spawn the algorithm run off the request thread, so the HTTP call can return immediately while the trading runtime continues asynchronously. Get system config from config. Config is the runtime configuration loader and validator that prepares broker credentials, strategy parameters, risk limits, and environment-specific settings before any components are instantiated. Algo from core. Algo is the orchestration object that composes the strategy, market data, order manager, and trade lifecycle pieces, and actually initializes and starts the trading run. This is the piece start Algo API hands control till after configuration is validated. Compared to other controllers in the codebase that import controller to handle request-level coordination, Start Algo API differs because it needs direct access to configuration and the Algo orchestration layer, and uses threading to launch a long-lived runtime rather than simply delegating to a controller for synchronous request handling. Start Algo API is the HTTP entry that triggers a live Algo run. When its post handler is invoked, it launches the framework startup sequence in the background and immediately returns a small JSON response that instructs the UI to redirect. Concretely, the handler spawns a new thread that invokes algo.startAlgo, so the request thread does not block while the engine initializes. The call to algo.startAlgo will perform the actual initialization steps you've seen elsewhere, checking the Algo running guard, fetching instruments, spinning up the trade manager thread and the strategy thread, and setting the running flag. After kicking off the background start, the handler loads runtime configuration by calling get systemconfig, which reads and parses the system JSON file. Build a redirect URL by appending the Algo started flag to the configured home URL, logs that redirect, and returns a JSON payload containing that URL. The returned redirect ties into Home API's logic, so the web UI will render the Algo started view when the browser follows the redirect. In short, Start Algo API coordinates the non-blocking launch of the trading engine and communicates that state change back to the front end via a config-to-ride redirect. Vinforb 30min_part 1 implements the signal generation half of the Bank Nifty opening range breakout strategy as a singleton subclass of base strategy. So only one instance runs, and it inherits the framework defaults for strategy wiring. Its constructor configures the strategy-specific parameters. It sets the product type to intraday MIS, an empty symbol list. It resolves Bank Nifty dynamically, stop/start/square off times using utils to get time of today, capital, and sizing fields, max trades per day, and other flags that tell the engine this is an FNO future strategy. The process method is the runtime entry. It restricts The imports wire the option selling strategy into the rest of the engine by bringing in the runtime, domain, and lifecycle pieces it needs to generate option selling signals, build trade objects, and hand them off for execution. Logging provides strategy-level observability, so runtime decisions and errors are recorded. Daytime supplies timestamping and time-based decision points used by expiry and intraday rules. Instruments gives access to instrument metadata and helpers for selecting option strikes and expiries, which is central to any option selling logic. Direction and product type are the canonical enums the framework uses to tag trade intent and order class, so trades created by option selling conform to the same segment/product conventions used throughout the engine. Recall order input perms relies on these canonical enums. Base strategy is the pluggable strategy contract option selling implements, so it can be wired into the strategy runner. Util supplies shared helper functions, rounding, price checks, small calculations, and formatting that keep strategy code concise. Trade is the domain model the strategy instantiates to represent an open position and its lifecycle metadata. Trade manager is the lifecycle controller the strategy delegates to when it wants to place, modify, or exit trades. This aligns with the trade manager _part 5 helpers you reviewed earlier. Compared to the other similar import blocks, this set follows the common pattern of including logging, datetime, base strategy, utils, and the domain enums, but differs by explicitly pulling in instruments in the trade class here, because option selling actively selects option instruments and constructs trade objects itself, whereas some other strategies only reference quotes or omitted direct trade instantiation. Option selling is a singleton subclass of base strategy that wires the option selling logic into the framework strategy layer and configures the strategy-level parameters that drive trade generation and lifecycle behavior. Its get instance and ___ enforce the singleton pattern and call base strategy. ___ with a strategy name, so it inherits the framework defaults, then overrides several fields to tailor this strategy. It sets product type to MIS, enables FNO behavior via isFNO, raises SL percentage to 50, sets capital and capital per set, restricts max trades per day to 2, and places its active window using utils that get time of today to define start timestamp, stop timestamp, and square off timestamp. Can trade today decides whether the strategy should run by consulting the expiry helpers and utils. It will return true only if today is either the weekly expiry day or the day before weekly expiry. Using utils is to the weekly expiry day, and utils is to the for weekly expiry day, and logs the decision. Processes the runtime entry called periodically by the engine. It first gates execution by time, no action before start timestamp, and by max trades per day, then derives the underlying instrument to use for strike calculations by asking utils to prepare monthly expiry future symbol for the Nifty monthly future and fetching its live quote via basestrategy.getQuote. If the quote is unavailable, it logs an error and stops. With a valid futures quote, it computes an ATM strike using utils.getNearStrikePrice with a 50-point multiple, logs the computed ATM, builds two weekly option symbols, 150 points above as a call, C, and 150 points below as a put, P, using utils.prepare weekly option symbol, and passes those symbols to generate trades. Generate trades calculates the number of lots via calculate lots per trade, fetches quotes for both option symbols through getQuote, logs and returns if either quote is missing, and then invokes generate trade for each option with the computed lots and each option's last traded price. Generate trade and the strategies should place trade logic live in the companion option selling implementation and will handle constructing trade objects and submitting them to the trade manager. The overall pattern and life cycle wiring mirror other singleton strategies, such as short straddle BNF, before 30 min and sample strategy, but option selling differs in its expiry-aware can trade today gating. Its use of the monthly futures price on Nifty to derive ATM strikes with a 50-point offset, and its specific two-leg option selling generation. Within the pluggable strategy layer, option selling _ part 2 is responsible for turning an option selling signal into a concrete trade object and deciding whether that trade should be sent to the order pipeline. When option selling _ part 1 determines a candidate option and calls generate trade constructs a trade tied to the supplied option symbol. It tags the trade with the strategy name, marks it as an option short position, and sets the product type from the strategy instance. The method marks the trade to be placed as a market order and records the requested entry price and an entry timestamp derived from the strategy's start timestamp, using utils to get epoch. Position sizing is computed by looking up instrument metadata via instruments.getInstrumentData by symbol to obtain the lot size and multiplying by the supplied number lots to set trade.quantity. Risk parameters are derived from the strategy configuration. Stop loss is calculated as the requested entry plus the configured SL percentage of that entry, rounded to the exchange price grid with utils that round to SC price. Target is left unset, 0, because this strategy uses no fixed profit target, and an intraday square-off epoch is set from the strategy's square-off timestamp. Once populated, the trade is handed to Trade Manager that add new trade, so the engine can persist it and start lifecycle handling, order placement, tracking, and exits. The should place trade override simply defers to base strategy that should place trade and returns true only if the base class allows placement, adding no additional gating logic. This mirrors the placement behavior used by short straddle BNF where the base checks govern whether a queued trade is eligible to be sent to the broker. Overall, option selling _ part 2 plays the builder and gatekeeper role in the end-to-end flow. It synthesizes trade details from strategy parameters, market prices, and instrument metadata, and then registers the trade with the trade manager for execution and tracking. The import setup, the minimal scaffolding sample strategy, needs to generate signals and hand them off into the framework's execution pipeline. Logging provides runtime diagnostics, so the strategy can emit info, warnings, and errors while running. Direction and product type bring in the domain enums that the strategy uses to describe trade side and the product segment when it builds signals and trade objects. Base strategy supplies the common strategy lifecycle and wiring that sample strategy extends for signal logic, and utils gives access to the small, strategy-facing helper routines, the same helpers we looked at in utils _ part 4, used for things like expiry and strike decisions. Trade and Trade Manager are the trade domain pieces used by the execution half. Trade is the in-memory trade representation the strategy constructs, and Trade Manager is the lifecycle/execution coordinator that the strategy will hand those trade objects to for order placement, tracking, and state transitions. Compared with the similar import lists you've seen elsewhere, this set is intentionally focused on strategy and trade lifecycle concerns. Other modules add datetime, quotes, or instruments when they need direct market feed or metadata access, whereas sample strategy limits itself to the core models. Base class and lifecycle utilities needed to demonstrate the signal trade manager flow within the STUSA Algo trade Python master _ clean framework. Sample strategy _ part 1 is a concrete example trading strategy that plugs into the framework by subclassing base strategy and demonstrating the full signal to trade setup for simple intraday equity breakouts. It enforces a singleton pattern via an _ instance holder and get instance, so only one sample strategy instance runs, then calls base strategy initialization with a strategy name to inherit common wiring, including trade manager registration and preloaded trades. During initialization, it configures strategy-level parameters. It chooses MIS as the product type, lists a small set of cash symbols to scan, sets a small SL and target percentage, Set start/stop/square off timestamps using utils to get time of today as provided by the shared utils layer, and sets capital, leverage, max trades per day, and is FNO to reflect a simple intraday equities approach. The process method is the signal generator. It first enforces the daily trade cap by comparing the current trades list populated by base strategy via trade manager to max trades per day, then iterates the configured symbols. For each symbol, it fetches a normalized quote via getQuote, which ultimately uses quotes.getQuote. Logs and skips if no quote is available, computes a tiny breakout band around the quote close by applying a 0.5% offset and normalizing with utils that round in its price, reads the last traded price, and decides direction equals long if the CMP exceeds the long breakout level, or short if it falls below the short breakout level. When a breakout is detected, it calls generate trade with the symbol, direction, breakout price, and CMP. Generate trade builds a trade object, tags it with the strategy name and direction, sets product type, marks it as a market placement candidate, stamps the trade timestamp using utils to get epoch on the strategy, start timestamp, and sizes the order by dividing calculate capital per trade. Inherited from base strategy by the breakout price, ensuring at least one share. The rest of trade finalization and lifecycle validation via should place trade, order creation, and handoff to trade manager/order manager is implemented in the paired sample strategy _ part 2 and base trade lifecycle pieces. Sample strategy _ part 1's role is therefore to produce clean, sized entry signals for the engine to validate and execute. This pattern mirrors the other example strategies, such as Benforb 30 min. Sample strategy _ part 2 is the execution side implementation that takes a breakout signal produced by a sample strategy _ part 1, converts it into a fully specified trade object with risk parameters, and hands a trade to the framework's lifecycle manager so it can be placed and tracked. When preparing the trade, it first computes a directional stop loss by anchoring to the breakout price and applying the strategy's SL percentage, using utils to round in a C price to normalize the price to exchange granularity. It then applies a defensive adjustment based on the current market price, CMP, so the stop does not end up on the wrong side of the market. Again, rounded via utils to round in SE price. The target is derived similarly from breakout price using the strategy's target percentage and rounded. The method also stamps the trade with an intraday square-off epoch using utils to get epoch on the strategy's square-off timestamp, so the engine can automatically exit its session end, and finally registers the trade with Trade Manager to add new trade, so the Order Manager and Trade Manager lifecycle routines will pick it up for placement, SL/target tracking, and persistence. The should place trade override first delegates to base strategy to should place trade, so the common gating logic, market window, per strategy limits, etc., runs. It then requires a non-null market tick and enforces a simple execution trigger. For long, the tick last traded price must have moved above the requested entry, and for short, it must have moved below the requested entry. This placement gating mirrors the pattern used in Benforb 30 min _ part 2 and ensures the strategy only converts queued trades into live orders when a market confirms the breakout. For short straddle BNF, these imports connect the strategy to the engine layers it needs. Logging provides the runtime diagnostics, and event traces the strategy will emit. Daytime supplies the time stamping and time-based decisions, such as marking entries, exits, and comparing against option expiries. Instruments gives access to instrument metadata and lookup utilities so the strategy can translate conceptual strikes and expiries into concrete exchange symbols, critical for option mechanics. Direction and product type bring in the domain enums the strategy uses when it constructs trade intent, side, and product routing. Base strategy is the superclass that wires the strategy into the framework's lifecycle and scheduling, the same inheritance pattern you saw in Benforb 30 min _ part 1. Util supplies shared helper routines. Recall the two small option-facing helpers we covered in utils _ part 4 live alongside this, and the strategy will call the broader utils for ancillary tasks. Trade is the domain object used to represent a planned execution with all its parameters. And Trade Manager is the execution/lifecycle handoff that accepts trade instances and runs order placement, monitoring, and exit logic. The piece start algo API ultimately causes to run once the algo is started. This grouping follows the common import pattern across strategies, pulling in models, instruments, utility, and trade management, but differs from some other strategies that also import real-time quotes or explicit timing helpers. The presence of instruments plus trade/trade manager here signals that short straddle BNF focuses on option symbol construction and full trade lifecycle handling. Short straddle BNF _ part 1 is a singleton subclass of base strategy that implements the signal generation and wiring for a short straddle on Bank Nifty. Only one instance can exist, same pattern used by Benforb 30 min and options selling, and the constructor overrides base strategy defaults to set strategy-specific parameters, such as product type, SL percentage, target percentage, start/stop/square-off timestamps. Using utils.get time of today, capital, leverage, max trades per day, and is F&O. Can trade today always returns true for this strategy. So the decision to act is driven by runtime checks and limits. The process method runs sequentially. It first enforces the start time and daily trade count limit, then builds the Bank Nifty monthly futures symbol using the shared utils helper and fetches its quote via base strategy.getQuote. If the futures quote is available, it computes the ATM strike by rounding the future's last traded price to the nearest configured strike interval using the nearest strike helper from utils_part 4. This strategy uses a 100-point granularity, logs the computed ATM, then builds the corresponding weekly option symbol for both CE and PE using the weekly options helper. Generate Trades computes how many lots to trade using the base strategy lot calculation, fetches quotes for both option symbols, aborts with a log if either option quote is missing, and otherwise invokes Generate Trade for each side. Generate Trade constructs a trade object for the option, tags it with the strategy name, marks it as short straddle BNF_part 2 is the execution-facing half that ties the short straddle BNF decision logic into the instrument metadata layer and the trade manager lifecycle. So when short straddle BNF_part 1 decides to create positions, the trades are constructed, sized, time-stamped, and handed off for execution and tracking. When a short option trade is generated here, a trade object is populated as an options short direction market entry. It sets the market order flag and records the requested entry as the last traded price, stamps the trade time using utils.getEpoch on the strategy start time, looks up instrument metadata via instruments.getInstrumentData by symbol to compute the quantity from the lot size and requested number of lots, and calculates the static stop loss by applying the strategy's SL percentage to the requested entry and normalizing the result with utils.roundNSC price. The trade target is left at 0, and the intraday square-off time is derived from the strategy's square-off timestamp. Finally, the populated trade is handed to Trade Manager.addNewTrade, so it is persisted and enters the framework's order and lifecycle machinery. Node instruments and Trade Manager calls produce console/file side effects as part of that handoff. The shouldPlaceTrade implementation in short straddle BNF_part 2 simply defers to base strategy.shouldPlaceTrade, so the strategy relies on the framework's generic gating, time windows, enabled flag, max trades per day, etc., without adding extra entry conditions. The getTrailingSL override implements a point-based trailing stop for short option positions. It guards against missing trade or price data, fetches the current last traded price via Trade Manager, the get. These imports load the small set of runtime pieces BrokerLogin API needs to act as the HTTP surface for broker authentication. Python's logging so handlers in this module can emit diagnostic and audit messages consistent with the rest of the app. Flask's method view, so BrokerLogin API, can be implemented as a class-based endpoint like other web-facing controls in the project. Flask's request and redirect helpers, so the endpoint can read incoming HTTP data, query parameters, posted form data, callbacks, and issue browser redirects during OAuth-style flows. And the core controller, so the HTTP layer can delegate broker-specific authentication logic, token exchange, and session setup to the centralized controller. Compared to other import groups in the codebase that also bring in JSON utilities, configuration loaders, broker model classes, or concrete broker adapters, such as Zerodha login, this module deliberately keeps its imports minimal and high level. It does not pull in broker implementation details itself, but relies on controller to encapsulate those concerns, mirroring the same separation of HTTP surface and business logic you saw with Start Algo API. BrokerLogin API implements the web-facing get endpoint that starts and completes the broker authentication handshake for the framework. When its get handler is invoked, it forwards the incoming query parameters to controller to handle broker login. Controller then reads the broker app configuration, constructs a broker app details instance, chooses the provider-specific login adapter, for example Zerodha login, and either returns a broker login URL for the browser to be sent to, or performs the request_token access for token exchange, and sets the controller's broker login handle. BrokerLogin API then issues an HTTP redirect response to whatever URL controller handle broker login returned, typically the broker's login page or the framework home URL with a logged-in flag. This keeps all broker-specific auth mechanics in controller and the provider adapters while providing a simple HTTP entry point the UI can call. Other components like base order manager, Base ticker, holdings API, and positions API obtain the authenticated broker handle later via controller, get broker login, and therefore depend on broker login API having completed this flow. Holdings API imports method view from Flask, so the endpoint is implemented as a class-based view, keeping its HTTP surface consistent with other web-facing controls in the framework. The standard JSON module is brought in to serialize and deserialize the holdings payloads exchanged over the REST surface, allowing the endpoint to return structured portfolio data to clients. Logging is used so the API can emit the same runtime diagnostics and audit-style messages the rest of the app produces when handling requests and reporting errors. Controller from core. Controller is imported so the web layer can delegate the actual business work. Auth-aware session lookup, broker adapter interaction, and holdings normalization to the centralized controller that knows how to talk to broker backends and map their data into the framework's domain objects. This combination mirrors the pattern used by broker login API, which also relied on method view, logging, and controller, but differs in that holdings API focuses on returning structured data and, therefore, does not pull in request/redirect helpers used during OAuth-style flows. When an HTTP GET arrives at the holdings endpoint, holdings API.get runs and drives a small, linear flow that bridges the web layer to the broker session already established by the framework. It first asks controller.get broker login for the current broker login instance, so it reuses the authenticated session that was created earlier by controller handle broker login. The flow broker login API triggers during user authentication. From that basic arrived object, it retrieves the broker handle via get broker handle. The broker handle is the runtime adapter that speaks to the brokerage and holds the active credentials/session context that base login stored during login. Holdings API then calls the broker handle's holdings method, which performs the network request to the broker to fetch the user's portfolio. The return holdings are logged with logging.info and serialized to JSON for the HTTP response. This follows the same pattern you saw in Positions API. The only functional difference is calling holdings instead of positions, and exists to provide the dashboard and other components a simple, authenticated REST surface for real-time portfolio data. These imports bring together the minimal pieces Positions API needs to present positions over HTTP and hand off the real work to the controller. Method view from Flask. .views provides the class-based endpoint pattern used throughout the web layer, so Positions API can be implemented like the other API classes. The JSON module is used to serialize and deserialize the position payloads the endpoint returns. Positions API returns structured JSON rather than rendering HTML templates. Logging supplies the same diagnostic and audit emission capability you saw used in broker login API, so runtime events and errors from this endpoint are recorded consistently with the rest of the app, and controller from core. Controller is the centralized business logic entry point that Positions API delegates to for fetching, normalizing, and preparing current position data before returning it to authenticated clients. This set mirrors the common pattern used by other endpoints that combine method view and controller, but it omits template or redirect helpers because its purpose is to return machine-readable position data. Positions API implements the HTTP surface for position data. When its GET handler is invoked by an authenticated client, it obtains the active broker session from controller, get broker login, and then asks that broker handle for the current positions, which triggers a network call into the broker adapter to retrieve live position information. Because controller.brokerLogin is created and populated during the broker login API handshake, Positions API relies on that base login back session being present to reach the broker. The broker handle it receives is the broker-specific object that encapsulates the API details and returns positions in a normalized form for the framework. After fetching positions, the get handler records a runtime info-level entry and returns the positions serialized as JSON to the caller. This pattern mirrors Holdings API. Both endpoints are simple method view entry points that delegate to the controller-backed broker handle to perform the actual broker I/O and then log and return the resulting JSON. Test.py pulls together the runtime helpers and the Zerodha-specific adapters so the harness can bring up a live feed, exercise order paths, and observe normalized quote data end-to-end. It uses the logging module so the harness emits the same diagnostic traces and runtime messages the rest of the app relies on for debugging and audits. And it uses the time module to paste the smoke test loop and insert short sleeps or timeouts while the ticker and order manager are being exercised. Controller is imported so the test can reuse the centralized broker/session orchestration and credential context, the same coordination point used by broker login API. Zerodha ticker is the real-time feed implementation the test instantiates to validate connectivity and tick delivery. while Zerodha Order Manager and Order let the harness create and submit representative orders against the Zerodha execution adapter and observe the lifecycle. Quotes is pulled in so the test can route raw ticks through the same quote normalization layer the engine expects, and util supplies small shared helpers, timestamping, formatting, and other utilitarian routines used by the test flow. This set of imports follows the project's usual pattern of combining logging and utils for common functionality, but differs from the other import lists you've seen by intentionally wiring in Zerodha-specific classes, Zerodha Ticker and Zerodha Order Manager, instead of the generic base order manager or the kite client used elsewhere. The addition of time is also specific to a test harness rather than production endpoints. Test is a small harness that exercises the ticker and order management layers, so you could do a quick smoke test of broker connectivity, real-time feed handling, and basic order workflows. Test ticker instantiates Zerodha ticker and starts its connection path. Recall Zerodha ticker, start ticker wires up the broker ticker callbacks and connects the kite ticker as you saw earlier. Then registers the test.ticker listener via base ticker.register listener, so incoming ticks will be dispatched to the listener. It then pauses briefly to let the socket settle, asks the ticker to subscribe to two sample symbols, SBN and Reliance, which triggers the instrument resolution logic you saw in instruments.get instrument data by symbol and Zerodha ticker.register symbols, waits a minute to collect live ticks, and finally stops the ticker to close the connection. Ticker listener is a simple callback that receives tick objects from the feed and writes their attributes to the log, so you can confirm the on_ticks tick data conversion and listener dispatch path is working. Test orders drives the order manager path. It creates a Zerodha order manager, reads a current market price using quotes to get CMP, computes a rounded limit price using utils.round NSE price, and places an entry order through Zerodha order manager.place order. After a pause, it attempts a modify via Zerodha order manager.modify order. Then it constructs and places an SL order and a target order. Using the direction and version logic you expect for protective and profit exits, logs the returned IDs, waits, cancels the target order if present, and then logs completion. Exercising place, modify, place SL, place target, and cancel flows so you can validate base order manager and Zerodha order manager interactions with the broker. Test miscellaneous exercises the order detail retrieval flow by creating a sample order, seeding it with a real-looking order ID, and calling Zerodha order manager to fetch and update all order details so the manager will query the broker for latest order state and update the order object. This validates the fetch and sync logic that trade manager and other lifecycle components rely on. Overall, test ties together Zerodha ticker, base ticker listener dispatch, instruments resolution, quotes, and utils helpers, and Zerodha order manager order APIs to give a compact end-to-end sanity check of the ticker and order layers you already inspected. The imports assemble the pieces this orchestration entry point needs to bridge instrument setup and strategy execution within the STUS Algo trade Python master_clean framework. Logging provides the same runtime diagnostics and event traces you saw earlier. Threading and time supply simple concurrency and scheduling primitives the entry point uses to run strategy loops or idle waits without blocking the process. Instruments gives access to the instrument metadata layer, so the entry point can load exchange symbols and lookups before any strategy runs. Recall instruments that fetch instrument from the architecture description. Trade Manager brings in the execution and lifecycle handoff, so once a strategy decides on trades, those Trade Manager capabilities are available to create, monitor, and manage orders. Finally, the concrete strategy classes Sample Strategy, Informed 30 Min, Option Selling, and Short Straddle BNF are imported, so the entry point can choose which strategy to instantiate and run. Short Straddle BNF is the strategy this file wires up for a short straddle on Bank Nifty, while the others are available as alternate or sample strategies. This pattern mirrors other modules that import instruments and Trade Manager, but differs by pulling in threading/time for runtime orchestration and by importing multiple concrete strategies here rather than only base strategy abstractions. Algo acts as the orchestration entry point that boots the runtime pieces needed for a trading run. Its start Algo method first uses a static is_Algo running flag to prevent duplicate starts and logs the activity. It then triggers instruments that fetch instruments, so the strategy layer has the instrument metadata required to resolve strikes, expiries, and exchange symbols. After that, it launches Trade Manager that run in a background thread, so the market data ticker, trade persistence, and order tracking loop are initialized. Trade Manager run is responsible for starting the ticker, loading prior trades, waiting for market open, and continuously managing orders. Start Algo then pauses briefly to give Trade Manager time to initialize and then starts the Short Straddle BNF singleton's run method in its own thread. Short Straddle BNF run follows the base strategy lifecycle you've already seen. Checking enabled state, market timings, can trade today, and then generating trade instances that are handed off to Trade Manager. Finally, start algo marks algo that is algo running as true and logs that the algo has started. The ordering ensures instrument metadata and the Trade Manager's market and execution plumbing are ready before the strategy begins producing trade intents. Zerodha ticker _ part 2 provides the thin adapter layer that turns kite ticker WebSocket callbacks into the framework's unified base ticker lifecycle hooks so the rest of the engine can react in a broker-agnostic way. When the kite ticker signals a successful connection, the on_connect implementation forwards that event into base ticker.onConnect so the common connection handling logic and any registered listeners are notified. When the socket closes, the on_close adapter sends the close code and reason into base ticker.onDisconnect. When an error is reported, on_error forwards the error details into base ticker.onError. Reconnect progress and terminal reconnect failure are handled similarly. On_reconnect relays the attempt count into base ticker.onReconnect, and on_connect invokes base ticker on max reconnect's attempt to indicate the ticker has exhausted automatic retries. Finally, broker order lifecycle messages from kite ticker arrive at on_update and are passed unchanged into base ticker on order update, so order managers or higher level components can process fills, modifications, or cancels. These methods are the callbacks, Zerodha ticker _ part 1 wires onto the kite ticker before starting the connection, allowing the project's trade manager, tests, and listeners to see the consistent stream of connection and order events. BrokerApp.json is the single source configuration the broker connectivity and authentication layers read to know which broker adapter to use and how to authenticate. It declares the broker identifier and the 3 credential-ish fields client ID, app key, and app secret that controller to handle broker login reads via get broker app config and copies into a broker app details instance, so the controller can instantiate the correct broker login adapter, for example Zerodha login, when the broker value is Zerodha. The file also contains redirect URL, which is the callback URL the broker's OAuth-style handshake will return to and which ties directly into the web-facing broker login API endpoint flow. Broker login API initiates the login. Controller delegates to the broker-specific login class using the broker app details values, and the redirect URL is used in that handshake, so the broker returns control to the framework. In the repository snapshot you inspected, the credential fields are set to dummy placeholders, signaling that these values are intended to be replaced with real client/app credentials and a reachable callback URL for an actual authentication run. Holidays.json is the canonical, standalone list of market closure dates the trading engine uses to know when the exchange is closed and normal trading activity must be suppressed. It is represented as a simple JSON array of ISO date strings for 2021 that correspond to national/exchange holidays, for example Republic Day, Holy, Good Friday, and other closures, and is intended to be read by the framework before runtime operations begin. At startup or when scheduling trading activity, the framework calls getHolidays to parse this file and return the list. The scheduler, risk controls, and the trade lifecycle manager consult that list to stop market data ingestion, prevent order placement, and to adjust session handling on days the market is closed. Unlike server.json and system.json, which are keyed objects containing a few runtime settings, holidays.json is a flat array of dates. It can also be extended to include per-day session metadata if needed, but the current file contains only date entries. Because holidays.json is standalone, it acts as a single source of truth for trading disabled days that the rest of the components, Algo, the ticker adapter such as Zerodha ticker _ part 2 via the scheduling/risk layer and order management routines, look up to enforce non-trading behavior. Server.json centralizes the runtime server settings the framework uses when Algo boots the HTTP and WebSocket endpoints, providing the values that tell the process which network port to bind, whether TLS should be enabled and which TLS port to use, and where on disk the runtime should place deployed artifacts and log files. At startup, the configuration loader function getServerConfig reads server.json and returns the parse configuration, so Algo and the server initialization path can consult the port and the enable SSL flag to decide whether to start playing HTTP or an SSL listener on the SSL port. Other runtime components then consume deploy_dr to know the target directory for deployment artifacts, the same value later assigned to the deploy_dr variable in the codebase, and logfile_dr as the location for runtime logs, compared with system.json, which only supplies a higher-level home URL used by UI/navigation logic. Server.json contains the concrete runtime and file system parameters the process needs to configure networking and local services. System.json is the single source place where the runtime announces the system's public base URL to the rest of the framework. It contains a home URL entry that components read at startup to know the canonical external address for building callbacks, redirects, and links. The framework's loader gets system config, opens system.json, and returns that JSON, so orchestration and broker-related pieces can concatenate paths against the declared home URL instead of hard-coding host/port. In the project's configuration pattern, system.json sits alongside server.json and brokerApp.json, but serves a different role. Server.json declares how the local server binds and where logs are written. BrokerApp.json holds broker identity and credential fields that controller handle broker login maps into a broker app details instance, including the broker redirect URL. And system.json supplies the logical public URL that those redirect endpoints and external integrations should use. Because system.json only provides the home URL, its purpose is narrowly scoped. Give a single, authoritative base URL that other modules use when constructing external-facing endpoints. Direction is the small domain model that gives the rest of the framework a single, canonical way to express trade-side semantics. The two named values capture whether position or order is intended to be a long or a short. Across the orchestration layers, such as Algo, the strategy implementations, the order management and execution code, and the trade lifecycle manager, components compare against direction constants instead of using ad hoc strings, so decisions about entries, exits, hedges, and risk controls remain consistent. Because direction is standalone, it has no runtime wiring like Zerodha ticker_part2 or the broker configuration read from brokerApp.json, but is referenced conceptually by the same pieces you exercise with test when orders are created or evaluated. The pattern behind direction is the same approach used by order type, product type, and segment. Each class enumerates a small closed set of domain values as named constants, so the rest of Stusa Algo trade Python_master_cleaned can be type safe and less error-prone when encoding exchange and strategy semantics. Direction differs only in scope and cardinality, modeling the binary side of a trade rather than order kinds, product categories, or market segments. Order status defines the canonical set of named states used across the order management and execution layers to represent where an order is in its life cycle. From the moment a placement request enters the system through validation and broker interaction to final outcomes like completion, cancellation, or rejection. It provides labels such as an initial request arrived state, a validation pending state, one or more pending/open states that reflect awaiting broker acknowledgement or trigger activation, a final complete state for fully filled orders, and terminal states for rejected or canceled orders. Algo and the higher-level orchestration create order objects that carry an order status field whose value is drawn from order status, broker adapters, the ones selected via brokerApp.json, and the ticker adapters are to ticker_part2 drive updates to that field as they report confirms, fills, triggers, or error responses. The test harness observes those transitions during smoke runs. Compare with trade state. Order status is more granular and focused specifically on order-level workflow steps, validation, and broker request/trigger phases, while trade state expresses broader trade lifecycle phases like created, active, or completed, with order type describing how an order should be executed, limit, market, stop variance. Order status describes what has happened to that order during execution and monitoring, enabling consistent logging, risk checks, and state-driven behavior across the engine. Order type is the small, standalone enumeration that the rest of the framework uses to name and normalize the execution intent of an order, so strategies. The order manager and broker adapters all speak the same language. When a strategy constructs an order intent during a trade decision, it picks one of the order type values to express whether it should execute immediately at market, wait for a limit price, or act as a stop-loss instruction, where a trigger price leads to either a market or a limit execution. That chosen order type then travels with the order through the order management and validation layers, which are test harness exercises against the broker connectivity, and finally the broker adapter. The adapter selected via the brokerApp.json-driven configuration maps the normalized order type into the broker-specific API field Zerodha or another broker specs. Order type follows the same pattern used by product type, order status, and trade exit reason. Each is a compact class of string constants used for cross-layer normalization. It differs from product type and order status by representing execution semantics, how to fill an order, rather than product segment or lifecycle state, and it specifically distinguishes plain market/limit execution from stop-loss variance, so the order manager and brokers can handle triggers and execution price behavior correctly. Product type is a tiny, centralized class that enumerates the product categories the trading engine uses when constructing and validating orders: the intraday margin product, the normal overnight product, and the delivery/cash product. Because the framework separates broker adapters from core logic, product type provides the canonical labels the order management and trade lifecycle layers attach to every order, so broker-specific encoders, for example. The Zerodha adapter the orchestrator wires up via broker_app.json can map them to the broker API's product parameter, and the risk/margin subsystem can apply the correct rules. When Algo or the test harness asks the order management layer to place a trade, the chosen product type influences margin calculation, whether the position may be carried overnight, and which exit/auto square-off rules apply. Product type follows the same simple constant pattern used by order type, direction, and segment. Each is a compact namespace of string values used across the codebase to avoid magic literals. It differs from order type in that it describes the order's billing/margin semantics rather than its execution mechanism, and it complements direction and segment by providing the product dimension that, together with side and segment, fully describes how an order should be routed and managed. Segment is a small, canonical model that enumerates the market/exchange segments the framework recognizes: equity, FNO, currency, and commodity, and it centralizes the single set of labels that instrument normalization, data ingestion, and order routing consult when they need to apply segment-specific behavior. When instruments are normalized or instrument metadata is looked up, segment values are attached to the instrument, so ticker adapters like Zerodha ticker_part2 and the ingestion layer present quotes with a consistent segment identity. The execution and order management code then uses the same segment labels to decide routing, margin/product rules, and any validations the trade lifecycle manager must enforce. Segment follows the same constant enum pattern used by order type, direction, and product type, a compact set of string constants referenced across the codebase rather than instantiated objects, but it is orthogonal to those. Order type and direction describe how an order should behave, product type describes contract/execution semantics, and segment describes where the instrument lives in the market structure. So the runtime composes segment with product type and order type to drive segment-aware risk controls and routing without scattering literal strings through Algo, the test harness, or other modules. Home API pulls and flasks class-based view helper method view, so the route handlers can be implemented as tidy, testable classes rather than plain functions, and it imports render_template and request, so the home endpoints can either render a simple HTML landing page and health/status UI, or inspect incoming HTTP details, query parameters, headers, and form data for lightweight diagnostic and status checks. Within the Stusogo Trade Python_clean framework that keeps the root interface purposely minimal and decoupled from the orchestration pieces. Other modules that expose API endpoints often import method view plus JSON, logging, and the core controller to perform broker orchestration and return machine-readable payloads, or import request plus redirect when they implement flow control. Home API instead uses render_template to serve a human-friendly landing view and request to read any caller-supplied metadata for health checks, following the same class-based view pattern but without pulling in controller or heavy JSON handling. Home API is the lightweight Flash view that serves the application's root landing pages and lets simple clients, the browser UI, monitoring probes, or smoke tests, verify runtime state by returning one of 3 HTML pages depending on URL query flags. As a method view, it implements a get handler that checks request query parameters for a logged-in indicator and an Algo started indicator. When logged in is present and true, it returns the index underscore HTML view, the page that exposes the Start Algo button tied to Start Algo API. When Algo started is present and true, it returns the index Algo started.html view, the page that shows the Algo is running and off for stop controls, and if neither flag is set, it returns the default index.html landing page. The behavioral link with Start Algo API is explicit. Start Algo API launches Algo.startAlgo in a background thread and responds with a redirect URL that appends the Algo started flag, so Home API will render the running state page. Similarly, the logged-in flag maps the post-login state the UI wants to present after broker authentication. Home API is intentionally minimal and stateless. Its job is purely presentation routing for basic status and UI entry, rather than orchestration or broker connectivity. So it lives standalone as the simple entry point for human and automated checks of the service. Index.html is the minimal landing template the web UI serves when a user has not yet authenticated a broker session. Its job within the Stus Algo Trade Master_clean project is to present a simple, friendly entry point that triggers the broker authentication flow so the rest of the trading dashboard and engine can be used. The document defines small, embedded style rules for a reusable button and a center alignment class, renders a blue heading that welcomes the user, and shows a single action button wired to a browser-side function named Login to Broker that navigates the browser to the local server's Zerodha broker login endpoint, so the backend's broker login API can perform the authentication handshake. Since Home API already handles which HTML landing page to return based on request flags and runtime state, index.html acts as the unauthenticated variant in that flow. The related templates index_html and index_started.html reuse the same visual styles but extend behavior. They load jQuery and perform AJAX posts to start and stop the algorithm engine, the start algo and stop algo client functions, and display running state text instead of a login button, whereas index.html purposefully remains static and focused solely on initiating the login redirect. The file contains no dynamic asset injection or live market UI itself. It simply funnels the user into the broker adapter's login route, so the broader engine layers, broker-specific connectivity, order manager, strategy layer, can be accessed once authentication completes. Index_started.html is the simple front-end view the user sees after an algorithm has been started. It plays the role of a lightweight runtime dashboard page in the overall Algo trading UI, showing the Algo's running status and offering a client side hook to stop the strategy by calling the backend API. The template sets up basic HTML metadata and reuses the shared inline styles for the .button and .center classes used across the other entry pages. Index_html and index.html then pulls in jQuery from a CDN so that the page can make AJAX calls. A small JavaScript routine named stopAlgo is defined that issues a post to the engine stop endpoint and reports the JSON response via a browser alert, so the page can command the engine to halt execution at runtime. The visible body renders a branded heading and a concise Algo is running status message centered on the page, presenting minimal runtime feedback to the operator. Remember the Home API we reviewed earlier that serves the app's landing pages? Index.html fits the same pattern as those templates. Index.html provides a start Algo routine and a start button, and index.html provides a login to broker navigation. So index_started.html is the counterpart used when the system is in the running state and needs a client-side stop control wired to the /apis/algo/stop endpoint. Index.html is the template Home API returns for authenticated users and acts as the minimal main dashboard after login. It declares a small set of page-wide styles for a reusable button and centered layout, pulls in jQuery for AJAX, and defines a client-side start Algo function that posts to the application's Algo start API. When the server responds to the post, the JavaScript looks for a redirect field in the JSON and navigates the browser there if present. If not, it presents a simple alert with the status and return data. The body renders a centered welcome header and a single start Algo button wired to start Algo. So clicking it is the UI action that kicks off the strategy/execution lifecycle handled by the order manager and trade lifecycle manager on the backend. The template follows the same visual and scripting pattern as index.html and index_started.html. Index.html provides the broker login entry, login to broker. Index_html is the authenticated entry point that triggers algorithm startup. And index_started.html represents the running state and offers a stop action, stop Algo. The file is standalone, uses the same simple styling and client-side AJAX approach as its siblings, and serves as the browser-side trigger that transitions the system from an authenticated idle state into active Algo execution. The import brings in the JSON encoder base class from Python's standard JSON library, so Trade Encoder can subclass it and provide a customized JSON serialization strategy for trade objects used by the Trade Lifecycle Manager. Since the file's job is to convert internal trade instances into portable representations for persistence and messaging, Trade Encoder derives from JSON encoder to override the default handling of objects the standard serializer can't natively encode, for example, date times, enum types like order type, /product type, or the nested domain objects. This is a narrower, intent-focused import compared with other modules that pull in the JSON module to call dumps/loads directly. Here the framework needs the encoder base class, so the custom encoder can be registered when the system serializes trades. A prior, simpler trade encoder in the project implemented default by returning an object's attribute dictionary, and this import is what enables that pattern of providing a pluggable, class-based JSON encoding implementation. Trade encoder is a tiny, focused serializer class that extends the standard JSON encoder, so the trade lifecycle manager and other modules can turn internal trade instances into a portable dictionary/JSON form for persistence, messaging, or intermodule transport. Conceptually, it overrides the encoder's default behavior to emit the trade object's attribute map, i.e., the set of its public fields and their values, rather than trying to encode the object as an opaque type, which produces a flat mapping whose keys match the trade class's fields such as trade ID, trading symbol, product type, entry order, SL order, target order, timestamps, and P&L attributes. That dictionary shape directly complements the manual deserializer implemented in Trade Manager Part 7's converts on a trade, which expects those specific field names to reconstruct a trade in its nested order objects. Similarly, the serialized product type, order type, and segment-like field align with the canonical enums we discussed earlier, order type, product type, segment. The implementation is standalone and intentionally minimal. It leverages Python's encoder machinery, the same import used elsewhere, to provide a predictable, framework-wide way to serialize trade instances into the portable format the rest of the system uses for storage and messaging. Trade exit reason is a small canonical enumeration that names the standard, human-readable reasons why the trade lifecycle manager and related modules mark a trade as closed. It centralizes the labels used by the trade lifecycle manager, order/execution modules, risk controls, logging, and analytics, so everyone in the system reports the same exit semantics. Conceptually, it contains constants for the typical exit events you care about in an algo trading flow. A stop loss being hit, a trailing stop loss being hit, a profit target being hit, an explicit square off by the system or user, and the two cancellation cases where a stop or a target is canceled. And those labels are what the rest of the engine stores and emits when a trade completes. The class follows the same lightweight pattern as trade state and order type, a centralized set of string labels that other components import and compare against. But whereas trade state captures where a trade is in its life cycle, trade exit reason captures why the life cycle ended. In practice, components like Trade Manager use these constants when transitioning a trade to completed status or when logging order management actions. For example, Trade Manager sets a trade to completed with one of these exit reasons and then calls its SL/target order helpers. And analytics and risk modules consume them to aggregate outcomes and enforce post-exit rules. Because trade exit reason is standalone and declarative, it keeps downstream code consistent and readable across the execution and lifecycle layers of the Algo trade Python master_clean framework. Trade state defines the canonical set of high-level lifecycle labels the engine uses to track where a trade sits in its life, so the trade lifecycle manager, order manager, and persistence/reconciliation logic can reason about transitions consistently. When a trade object is instantiated, it starts with a created label, which marks an in-memory record that has been constructed but not yet advanced. The engine and order manager move that trade to active when entry execution completes and the position is live. When an exit completes successfully, the trade is marked completed and the lifecycle manager finalizes timestamps, P&L, and exit fields, often recording a trade exit reason. If the trade is aborted before becoming active or explicitly stopped, it moves to canceled. Disabled is used to mark trades that are intentionally prevented from progressing by risk rules or operator configuration. The pattern here mirrors the simple constant enumeration approach used by order status and trade exit reason, but trade state is focused on the overall trade level lifecycle, rather than individual order lifecycle or exit cause, and is a single attribute the rest of the system inspects to gate state transitions, persist final records, and drive downstream reconciliation.